Yes. Yes, the John von Neumann Society is established in 1968, and we bearing Neumann name from this year. It means that we early started to remember and work for his reputation. It was the first professional computer associate in Hungary. Today we are four different topics what we are focusing. One is the improve the digital competence, digital literacy in Hungary is very important these days. We have naturally many professional interest group what is working different area of the computer science. We are responsible for all the competition, informatic competition for students. It means a very huge talent development and competition preparation work. Last week was in Szeged, this year informatic Olympic for Worldwide Informatic Olympics, and we initiated this one, and we got the organization possibility because of this Neumann memorial year. And we have a very huge museum in Szeged is collecting all the computer and telecommunication equipment from the beginning to today's. I think is a unique museum because it includes not only the Western but the Eastern computers as well. And our society not only this year keeping the memory of the John von Neumann. We have in this museum a Neumann room with original documents of John von Neumann. There are many institutes has a Neumann name. We are continuously make a connection them and working with them. Continuously, we have researches, presentation on von Neumann life and works, and every year we have a laying process in the birth house of the Neumann. Here is a picture on it, and we arrived this memorial year, and some point I would like to show from this day. First of all, some company and institute supported this year. This is the reason that we are able to organize a number of programs. It's very important. This is the first exhibition in the Fasori High School, where the Neumann and some other well-known scientists graduated. In this school, it was a so-called milieu exhibition with the Neumann family furnitures and painting and other reliquias. And this is what the premiere of the poster exhibition, but will be a traveling exhibition, is traveling in the countryside to show the Neumann life and works everywhere in the Hungary. Yes, it was a very interesting that we asked for artists to make artworks homage on Neumann words, and we got about 130 artworks, and several of exhibition organized in this year, and I only mentioned this city poster exhibition in the city of the Budapest, or the other exhibition was opened by Karikó Katalin, and the artist was very happy to meet her. And on the other hand, the Karikó Katalin got this year NEUMANN Professor Award, that we established together with Hungarian Budapest Technical University. And I think this is a very prestigious award because 2 Nobel Prize winners, 3 Abel Prize winners got already this award, and hope that the Karikó Katalin is a potential candidate for the next Nobel Prize. We issued a nice bilingual album by István Hargittai and Balázs. István is here, and as I recognize that somebody already dedicated, or asked for dedication from him. Everyone get a copy of this book, thanks to the Ministry of the Culture and Innovation. They supported to provide these books to the audience here. And not only this book, but we have a memorial medal, issued by the Hungarian National Bank. Again, we can, if you are interested, we have some coin here, and we can give who somebody would like to buy this one. There is a so-called Nobel Prize winners park in Balatonfüred. The Lake Balaton is well known in Hungary. There is this park, and we agreed the mayor and the assembly of the town that a Neumann memorial tree was printing in June. I think again an extraordinary event what he can order. I would like to underline not only the scientific approach, but would like to show the wider audience the importance of the von Neumann work. Yes, and only it was only some highlight of this year. If somebody interested in this homepage can recognize the past and the next events, about 100 events organized in this year. I think I hope it is a good memory of the John von Neumann and his excellent work. In this homepage, not only the event, but we try to collect all the reports, books, graphics, briefs, and others what is mentioned or show from Neumann. And this is the ambition that end of the year we have a complete collection of the memory of the John von Neumann. This is a short overview that this how can we arrive this conference. I mentioned that thanks to the Hungarian Academy of Science we are able to have in this nice environment, in this nice building, and main patron of the conference of Tamás Freund, the president of the Academy, and thanks to him. I think we can organize a very contentful conference. And here is the program. The first period, some greeting and the overview of the John Neumann works. And first of all, I would like to invite you to this stage to Kollár Péter, the General Secretary of the Academy, who will make some opening thought on this conference. He's a Széchenyi Prize winner, civil engineer, and is very well known in the Hungarian academy environment. Please.
Thank you very much. Dear participants, distinguished guests, dear colleagues, ladies and gentlemen. When I think of John von Neumann, the following story told me in the 90s that always comes to my mind. Von Neumann making a derivation during a university lecture, he stopped and said, "It is obvious." Is it obvious? Then he left the room, he returned 15 minutes later saying, "Yes, it's obvious." And he continued the lecture. I must add that the story was told me at an American university where one building was named after the Hungarian mathematician Pólyai, and in those days there was an exhibition on another one, Szegő. Well, searching the internet, you will find that the same story told in relation to several famous mathematicians. But for me, this story is about John von Neumann. And although the anecdote may not be authentic, it clearly reflects the admiration that is widely held for the genius of John von Neumann, who was born 120 years ago. The many stories, humorous anecdotes, and ideas attributed to von Neumann show that von Neumann's name is synonymous with the concept of the genius, even among laypersons. However, it is not the reason that we have gathered here today at the Hungarian Academy of Sciences. Rather, because professional scientists also regarded him as a genius of exceptional brilliance, and still do so today. The Hungarian mathematician Alfred Rényi had this to say about him: "Mathematicians prove what they can prove. Von Neumann proves what he wants to prove." Dear ladies and gentlemen, dear fellow researchers, at the first World Conference of Science Journalists held in Tokyo back in 1992, participants were asked to fill out a questionnaire to rank the scientists who they believed had the greatest impact on the 20th century. The result of the survey was that Einstein was placed first, Watson and Crick, the discoverers of the DNA double helix, came in second, and John von Neumann came in third, whose name was and still is associated with the word computer. And that's not surprising. After all, essentially, all our computers and mobile phones are based on the von Neumann architecture. But a genius can achieve greatness in any field, from mathematics to quantum physics, through game theory to the theory of intelligent, self-replicating automata. Von Neumann's output and contribution were outstanding. His essay, "Can we survive technology?" resonates with us today as a sort of von Neumann's prophecy, especially when we think of artificial intelligence and the prospect of the technological singularity. The science writer and von Neumann's biographer, Ananyo Bhattacharya, recently spoke about Neumann's genius in an interview. Quote, "He brought his insight, rationality, and logical thinking to bear in an attempt to provide answers to questions that arose in countless fields. He always started from the facts, but he examined the world as a whole in its entirety." End of quote. This short description not only sheds light on von Neumann's character, but on the universal and timeless duty of all scientists. In this sense, he he's a great model for us all. The subfields of science cannot exist without others. During our own research work, we must constantly refer to and interact with other fields which should have a major impact on our research. Dear colleagues, today's conference is one of the main events of the John von Neumann 120 commemorative year, an event that has brought us together from all over the world out of a deep-felt respect and admiration for the genius of John von Neumann. The Hungarian Academy of Sciences is delighted to be able to host this celebratory event and has, through the members of the section of mathematics and the section of engineering sciences, provided financial and professional support toward the high-quality program of the John von Neumann Computer Science Society. Neumann's legacy is an obligation to ensure that our meeting today will be more than just a commemoration, but also an opportunity to look to the future purposefully and responsibly. You may ask, how can this be achieved at a conference? The answer may be that through interaction. And an example of someone who embodied this idea was John von Neumann himself, a man who, besides possessing a superb intellect, was also a remarkable manager, someone who was able to work together with people of many different talents. An international conference is not only a forum for presenting the latest scientific facts and data, but can also be a fertile venue for personal interaction, for giving birth to scientific collaborations, interactions that have the potential to shape the history of science. There is a good example of just such an interaction in von Neumann's own life. When he had a chance encounter with Hermann Goldstein on the platform of a train station in the summer of 1944, an encounter that ultimately led to critical development in the computer. Before that encounter, von Neumann had seen several electromechanical computers, but he had no idea that the first fully electronic machine, the ENIAC, had been developed at the University of Pennsylvania. However, Hermann Goldstein, the young mathematician, recognized von Neumann on the platform of the railway station. He walked up to him, engaged him in conversation, and mentioned the machine to him. From that moment, von Neumann became involved in the development of the computer, and today we know what a fundamental role he played in this process and just how important that machine has been in the history of mankind. Perhaps an international conference can function as a platform akin to the one at the train station back then. We have gathered here on this platform, if you will, from different parts of the world, from different subfields of our discipline, and before we set off on our individual journeys again, we have a chance to talk to each other while standing on this platform. And from our encounters and conversations with each other, something may be born that will still be discussed at a conference sometimes in the future. Dear ladies and gentlemen, John von Neumann loved intellectual encounters, and we also know that he loved to read literature. And he especially loved Dickens. So allow me to conclude my greeting by paraphrasing Dickens. It is required of all persons that the spirit within them should influence their fellow men and their environment. And if that spirit goes not forth in life, it is condemned to do so after death. Yes, von Neumann's genius is reflected in the fact that he influenced his fellow men and women as well as his environment in his own lifetime. And then 120 years after his birth and nearly 70 years after his death, his influence is still being felt and is relevant today, as indeed is shown by this very event that we are gathering at today. Thank you very much for your kind attention. One more word, just I have to apologize because I have commitments at the university and I must go back there to deliver a lecture with a few derivations. So thank you very much.
So, Professor, I would like to say thank you and give a coin to remember this.
Thank you very much.
Okay, thank you for the presentation. And so, okay, I hope it's working already. Yes, the next greeting should be the Balázs Hankó, the State Secretary of the Ministry of the Culture and Innovation, but they have similar commitment what the professor saying. You know that in the governmental sector, the higher powers has a call, and the government guy should go, and therefore this morning I got the SMS from the sales secretary that he is not able to attend. But on the other hand, his dedication to this conference showed that they supported to provide you these books. I hope it is a good sign of the importance of this conference. The next greeting will be on video. The Marina von Neumann-Wittmann, daughter of the von Neumann, sent a short greeting to you. She is an economist. She is a professor of the Michigan University of Michigan, and she was board member many big corporations in USA, and she was consultant for the President Nixon. It means that she is not only the daughter of the Neumann, but herself is an eminent science, and she is a honorary patron of this year. She knows all the events. We regularly inform her on these things, and please show the video of Marina.
It's a pleasure to be asked to make a few opening remarks on this occasion of the 120th anniversary of my father, John von Neumann. Since he died so young at the age of 52, it's very hard for me to recognize that this is the 120th legacy year, but I am very pleased that his contributions are being recognized in this way so long after he lived. And of course, I'm very grateful to you and your organization for making this possible.
Okay, thank you. And last greeting also in video is coming from the Robert De Graaf, who is a past director of the International Advanced Studies, and it was the institute where the Neumann works and a long period. And Robert De Graaf is today Minister of Education and Culture and Science in Netherlands, and it is a very, and he awarded the Spinoza Prize, what is the highest scientific award in Netherlands. It means that again is not only the president of institute and minister, but really a scientist. And yes, there's this Internal Advanced Studies is in Princeton, US, and established in 1930, and von Neumann worked there from 1933, and he was one of the first professor. Among the other well-known scientists like Einstein, Oppenheimer, Gödel, and who emigrated from Europe to the US, and it was really a scientific and theoretic center of the USA, and make some advice and development for the US government as well. Please show the...
Hello everyone. I'm going to be honest with you. A video of approximately 2 minutes is not nearly enough time to sum up what John von Neumann meant to the scientific world and to our society at large. He was a brilliant mathematician, physicist and engineer, and his list of accomplishments in all of those fields is very long indeed. He established game theory, for instance, and built the foundations of quantum mechanics. I would even go so far as to say that von Neumann might have been a greater genius than Albert Einstein. He wasn't the only brilliant mind that Hungary brought forth during that time. Von Neumann belonged to a group of influential scientists known as the Martians, a joke by one of their members, physicist Leo Szilard, who once said that intelligent alien life is already among us. They just call themselves Hungarians. Abraham Flexner, the founding father of the Institute for Advanced Study in Princeton, the United States, wanted to acquire some of this intelligent life, including John von Neumann, for his institute. A place where the greatest academic stars could ponder deep problems undisturbed, as far away as possible from everyday issues and practical applications. A place where you could go on an unhindered pursuit of knowledge. An academic paradise, where countless discoveries were made and I had the privilege to call home for several years. To walk the halls where von Neumann once could be found. To be in the same environment that inspired him all those years ago. It was there at the Institute that von Neumann and his team designed, built and programmed an electronical digital computer, ultimately laying down the internal infrastructure for our modern-day computing devices. In fact, the building in which von Neumann developed that first modern computer, using the famous von Neumann architecture, now houses the Institute's nursery school. I always thought to be very fitting, since it's the place where computing also took its very first steps. Ladies and gentlemen, as I said, around 2 minutes is simply not enough time to list all of von Neumann's accomplishments, to really capture what he meant for the scientific world. Thankfully, all of you have more time to reflect on his legacy today. And you not only get to look back, but also look ahead at all the technological innovations we currently have and what is to follow in the future. Looking at all those technological marvels, building forth on von Neumann's work, we now need a GPS for the digital world more than ever. So please keep doing your important work, and I hope you all have a wonderful and inspiring symposium.
Okay, thank you. I think that it's good to hear these both videos, because I think it's a nice word, including the General Secretary as well. I think it was the nice opening of this conference, and after this greetings and opening speech, we are turning to the presentation. The first presenter is Miklós Rédei, who is professor of philosophy at the London School of Economics and Political Science. His specialization for the foundational and philosophical problems of the modern physics, including the quantum mechanics and quantum field of theory. And he was co-editor of the book titled John von Neumann and the Foundation of the Quantum Physics, and he is well known on the editor of the John von Neumann selected letters as well. Miklos, please.
Thank you. Thank you very much. Do you hear me? Thank you for the invitation to talk at this conference. It's a great honor and it's a privilege, and I'm very pleased to be allowed here to talk about John von Neumann's work. Talking about John von Neumann's work in general is a huge challenge. It's a scarily huge challenge, simply because his work is enormous, both in extent and in depth. So I do not really hope to be able to meet that challenge in a very substantial manner, but I'm trying to do my best, and I'm going to try this according to this schedule and outline. First, I'd like to say a couple of words about von Neumann's work in general, what type of work it was. These will be very general comments on von Neumann's work in general. And then saying something about von Neumann's attitude towards the Hilbert program. And this will be followed by some comments on what he did on the mathematical foundations of quantum mechanics. And in the second part of this talk, I will let von Neumann's contemporaries, colleagues, talk about what von Neumann did together with them on several issues in several fields, like the Manhattan Project. Hans Bethe will be speaking. I copied short video clips from the von Neumann documentary, which was prepared by the American Mathematical Society after von Neumann's death. And I will let Hermann Goldstein talk about the Institute of Advanced Study Computer Development, and Oscar Morgenstern about von Neumann's work on game theory. And finally, we will hear how Strauss, the chairman of the Atomic Energy Commission, talks about von Neumann as the advisor to the US government. This is the plan. I'd like to start by quoting another Hungarian-born famous mathematician, Peter Lax, who writes in the foreword to the John von Neumann selected letters, which has already been mentioned, which I had the pleasure to edit, the following. To gain a measure of von Neumann's achievements, consider that had he lived a normal span of years, he would certainly have been a recipient of a Nobel Prize in economics. And if there were Nobel Prizes in computer science and mathematics, he would have been honored by these too. So von Neumann should be thought of as a triple Nobel laureate, or possibly a 3.5-fold winner for his work in physics, in particular quantum mechanics. Quite serious words about the fellow mathematician. Peter Lax knew von Neumann personally. When Peter Lax moved to the US, he was introduced to John von Neumann. I also would like to quote from a possibly less well-known source, from the transcript of the hearings before the Senate of the Joint Committee on Atomic Energy. John von Neumann was interviewed by the Senate because he was appointed after the war as one of the Atomic Energy Commissioners, and that required confirmation by the Senate. And one of the senators, Senator Jackson, says the following about John von Neumann. I hope that your fertile mind, which is an invaluable resource of our country's security, will be used wisely by this country so that the full scientific talents which you possess can be fully exploited. I sincerely believe that our future security may well depend on the extent to which we exercise good judgment in using your scientific know-how. From what I know of your past record, it would indicate not only the great scientific and mathematical genius that you possess, but to my knowledge, a very unique arrangement that goes with it, good common sense and good judgment. These remarks by Senator Jackson, I think, are very important and indeed show that von Neumann was extraordinary, not in the sense only that he was a scientific genius, but that he had something else in addition to that, which doesn't fit well our stereotype of a great mathematician. The stereotype of a great mathematician is that he's a great mind, his analytic skills are extraordinary, but when it comes to practical everyday matters, he's quite lost. He doesn't know what to do, or if he thinks he knows, but he doesn't. But von Neumann was very different. He, in addition to being capable of analyzing things in a very clear manner, systematic manner, he had an almost engineering-like attitude towards practical matters and also to everyday matters. And this is why he was sought after very extensively as an advisor. And if you ever have a look at the von Neumann's selected letter volume, you will see letters there in which he expresses his views in response to questions about all sorts of issues, like what would be a good place in a university structure of a computer science department? What should be the training of engineers like at Harvard University? What kind of arrangements should an institute like the Institute of Advanced Study put in place in order to regulate the working times of the scientists? All sorts of everyday managerial issues, and he was very willing to give advice, and we will see how this advice was appreciated by those who received them. Now, to von Neumann's work, properly speaking. When you have a look at what he did, then you see that there are two strains of his work. On the one hand, there is the abstract axiomatic one, and on the other hand, there is the very concrete and opportunistic one. The abstract axiomatic includes his work on axiomatic set theory, which was his PhD work, his work on the Hilbert program, and then his work in different subfields in mathematics, like measure theory, ergodic theory, about which we are going to hear later from Professor Sass, lattice theory, continuous geometry, spectral theory, topological algebras. I'm going to say a bit more about these things, foundations of quantum mechanics, and game theory. His work in these areas is very abstract and axiomatic. On the other hand, his work in computer development, numerical analysis, weather forecast, detonations, directed detonations in particular, weapons design, simulations and modeling in general, and consulting and advice is very concrete, very opportunistic, very down to earth. So there are these two strains in von Neumann's work, easily distinguishable. And what is remarkable in addition to that, that there is a great harmony between these two strains, by which I mean that his work in abstract mathematics is very non-speculative in some sense. We will see in what sense a bit later. It is informed, motivated, influenced frequently by science, by the problem situations in the sciences, by the potential application in the sciences, and by real-world problems. On the other hand, the concrete, the opportunistic work is influenced by the abstract thinking, by the abstract results, and this will become also, it is very clear when it comes, for instance, to the computer development. So two strains in general of von Neumann's work, the abstract, axiomatic, concrete, and opportunistic, but these are in great harmony. They influence each other in a very fruitful manner. And that, I think, is quite unique. I'm not aware of any mathematician or any scientist who would have embodied this kind of harmony to the extent he did. Okay, now I'd like to talk about some of his work in some specific fields. Von Neumann wrote his PhD on axiomatic set theory. Approaches to axiomatic set theory were motivated by the crisis in mathematics at the turn of the 19th to the 20th century, which were prompted by the famous paradoxes in naive set theory, for instance, the Russell's paradox. So von Neumann wrote his first substantial papers on axiomatic set theory, and a closely related problem or issue which was motivated by the paradoxes in naive set theory was the Hilbert program. Hilbert came up with the idea of somehow designing a language which is expressive enough to state all mathematics in it and show that in that language, in that logic, contradictions cannot be derived. Roughly, in a nutshell, this is the Hilbert program. In von Neumann's work, the Hilbert program is the following. Hilbert came forward with the following ingenious idea to justify classical pre-intuitionistic mathematics. Even in the intuitionistic system, it is possible to give a rigorous account of how classical mathematics operates. That is, one can describe how the classical system works, although one cannot justify its workings. It might therefore be possible to demonstrate intuitionistically that classical procedures can never lead into contradictions. It was clear that such a proof would be very difficult, but there were certain indications how it might be attempted. Had this scheme worked, it would have provided a most remarkable justification of classical mathematics on the basis of the opposing intuitionistic system itself. And von Neumann himself worked on the Hilbert program. He tried to accomplish it. But as it turned out, this program could not be accomplished. The turning point in the Hilbert program was the famous Königsberg conference in 1930 between the 5th and 7th of September, which von Neumann attended. He was one of the three major speakers who were addressing philosophical problems of mathematics. The other two speakers were Rudolf Carnap, the leading figure in the logical positivist movement in Vienna. The conference was organized by the logical positivists, by the Vienna group and the Berlin group. Carnap was talking about the logical approach to logicism, the logical approach to mathematics, which attempted to reduce mathematics to logic. Hayting, the intuitionist figure, was talking about intuitionism, and John von Neumann was talking about the Hilbert program, essentially. And it was in that conference that Gödel announced the first incompleteness theorem, which von Neumann got interested in immediately. He pressed Gödel for further details. And a couple of weeks later, when he returned to Berlin, von Neumann at that time was a Privatdozent in Berlin, he wrote the following letter to Gödel. Dear Mr. Gödel, I have recently concerned myself again with logic, using the methods you have employed so successfully in order to exhibit undecidable properties. In doing so, I achieved a result that seems to me to be remarkable. Namely, I was able to show that the consistency of mathematics is unprovable. When is your paper going to appear? The paper which is containing the first incompleteness theorem. And when are proof sheets going to be available? This is also of technical interest to me, as I would like to follow you as closely as possible, both substantively and notationally, and on the other hand, I would like to publish as soon as possible. Hoping for your answer by return mail and to see you again very soon. So von Neumann, in today's terminology, proved independently what is called the second incompleteness theorem of Gödel. And the reason why we call it the second incompleteness theorem of Gödel is because, unfortunately for von Neumann, by the time Gödel had received von Neumann's letter, he had already submitted his paper containing the second incompleteness theorem. And he wrote this to von Neumann, to which von Neumann replies in this letter, essentially a week later, November 29, 1930, Many thanks for your letter and your reprint, as you have established the theorem on the unprovability of consistency as a natural continuation and deepening of your earlier results. I clearly won't publish on this subject. And he never did. He really never did. He regarded Gödel as being an exceptional figure in the history of logic, compared him even to Aristotle, and he says logic will never be the same again. Neumann continues, thus I think that your result has solved negatively the foundational question. There is no rigorous justification for classical mathematics. What sense to attribute to our hope, according to which it is de facto consistent, I do not know. But in my view, that doesn't change the completed fact. A quite remarkable moment, both in the life of Neumann and also, I think, in the history of mathematics, when the leading mathematician of the age, in view of these two theorems, especially of the second one, which he himself also proved, to the question, what is your reason to believing that classical mathematics is okay? He says, I have no idea. Quite remarkable, I think. Von Neumann also expressed this view, namely that the incompleteness theorems of Gödel mean the end of the Hilbert program, in another letter from which I would like to quote, which he wrote to Rudolf Carnap about half a year later, in which Carnap and Neumann discuss the proceedings of the Königsberg Conference. And then von Neumann says, I'm today of the opinion that first, Gödel has shown the unrealizability of the Hilbert program, and second, there is no more reason to reject intuitionism, and he adds to it, which I think is remarkable. I hope there are not many intuitionists here in the room. He says, if one disregards the aesthetic issue, which in practice will also for me to be the decisive factor, saying essentially that intuitionism is ugly, and I'm not going to follow it because it binds my hands, and I'm going to proceed in my mathematical research on the assumption that classical mathematics and pure existence proofs, for instance, are okay, as long as someone displays a contradiction in the foundations. Therefore, I consider the state of the foundational discussion in Königsberg to be outdated, for Gödel's fundamental discoveries have brought the question to a completely different level. I know that Gödel is much more careful in the evaluation of his results, but in my opinion, on this point, he does not see the connections correctly. I would like to emphasize nothing in Hilbert's aims is false. Could they be carried out, then it would follow from them absolutely what he claims. But they cannot be carried out. This I know only since September 1930. Another remarkable part of this letter is, which is a separate story, namely that von Neumann says here that Gödel views his results slightly differently. Gödel didn't think at that time that the incompleteness theorems are a death spell for the Hilbert program. Gödel was much more careful, but later on he changed his mind and he accepted essentially von Neumann's position. And it's an interesting question to which I don't really have the answer, why von Neumann and Gödel at that time disagreed so strongly, but there is evidence that they disagreed very substantially. So this is von Neumann's story with respect to the Hilbert program, very abstract mathematics. And from the failure of the program, von Neumann drew a very strong conclusion. Namely, he took the position that mathematical rigor is not a priori, it is historically changeable. Quote from a paper which is von Neumann's only paper in which he explicitly addresses philosophical issues related to mathematics, The Mathematician, Collected Works, Volume 1, if you're interested. He says there, the variability of the concept of rigor shows that something else besides mathematical abstraction must enter into the makeup of mathematics. And he adds to this that some of the best inspirations of modern mathematics, I believe the best ones, clearly originated in the natural science. So von Neumann, partly as a result of the failure of the Hilbert program, embraces a concept of mathematics, or a view of mathematics, if you want to call it a philosophy of mathematics, you might want to do that, which is empiricist to a large degree, which is a bit surprising in view of his very abstract work on axiomatic set theory, but this is the conclusion he came to from the 1930s on. So he views mathematics not as something a priori, but something which emerges from our dealing with nature and with society as well. And when we are intending to describe nature and social phenomena in a quantitatively precise manner, we are led to creating mathematical concepts which are suitable for that. This is how mathematics, in his view, emerges. This is a view of mathematics which was not shared very widely, not even by his close colleagues. It is very well known that Wigner, for instance, had a different view of mathematics. On the basis of von Neumann's empiricist-leaning mathematical concept, it's not surprising, is it, that mathematics is applicable in natural sciences, because it's coming from there. How could it be otherwise? It's not at all surprising. Whereas Wigner famously said that the applicability of mathematics in the natural sciences is very close to a mystery which we cannot explain, and he added, which we also do not deserve. So this is not an easily embraceable, not an easily acceptable position, but that was his position. And this position influenced also his mathematical work. And this is what I meant by his even abstract mathematical work not being speculative. A lot of what he did in abstract mathematics was motivated by the problems in the sciences or by the problems of the social world. Quantum mechanics and game theory are prime examples of this, and I'm going to talk about this a bit later, but before then, one more quotation which I think is interesting because it is a sort of advice which is still valid today for practicing mathematicians, and I do see some practicing mathematicians here in the audience. Von Neumann's empirical attitude towards mathematics includes the following advice. As a mathematical discipline travels far from its empirical source, or still more, if it is a second and third generation only indirectly inspired by ideas coming from reality, it is beset with very grave dangers. It becomes more and more purely aestheticizing, more and more purely larpular, and this need not be bad if the field is surrounded by correlated subjects which still have closer empirical connections. But there is a grave danger that the subject will develop along the line of least resistance, that the stream, so far from its source, will separate into a multitude of insignificant branches, and that the discipline will become a disorganized mess of details and complexities. In other words, at a great distance from its empirical source, or after much abstract inbreeding, a mathematical subject is in danger of degeneration. Whenever this stage is reached, the only remedy seems to me to be the rejuvenating return to the source, the re-injection of more or less directly empirical ideas. Very clear talk. It's a kind of advice for mathematicians to be aware of a danger which he regarded as a great danger. A prime example of von Neumann's work, which was motivated by the empirical sciences, is his work on the mathematical foundations of quantum theory, which I'd like to talk about now in the next part. His work on the mathematical foundations of quantum theory consists of two periods. The first period is between 1926 and 1932, The 1926 is the year when von Neumann goes to Göttingen to work as Hilbert's assistant on the Rockefeller Fellowship, apparently with the intention of pursuing the Hilbert program further. And 1932 is the year when his famous book on the mathematical foundations of quantum mechanics is published by Springer University. But when von Neumann arrived in Göttingen in 1926, in that academic year, Hilbert was lecturing on the mathematical foundations of quantum theory. And it was customary at that time that the assistant of the professor was sitting in the lecture, took notes, and on the basis of these, they made joint publications. And this is what happened also to John von Neumann. And they, Hilbert, him, and another assistant, Nordheim, wrote a joint paper on the mathematical foundations of quantum mechanics. It was published in 1926. And this was a remarkable paper for two reasons, at least. First, because that was the first attempt to axiomatize quantum mechanics. Remember that quantum mechanics was being born around this time. It was a very fresh, young discipline at that time. And this paper was an attempt to axiomatize quantum mechanics. That was the first attempt, and it was published in the Mathematische Annalen, which was the leading journal in mathematics. So the first remarkable thing about the paper is that this is the first axiomatization. The second remarkable feature of that paper is what is at the very end of the paper, in which the authors say that, I'm paraphrasing, not quoting, we are not entirely sure that what we are doing here makes sense, but it's mathematically meaningful. This is what they explicitly say, which is, I think, quite surprising. And then they also say that we hope to return to some of these issues in later publications, and they refer to a forthcoming paper by John von Neumann on mathematical foundations of quantum mechanics. And von Neumann published then, after this joint paper, 3 papers in which he was the sole author, in which he worked out what we call the Hilbert space formalism of quantum mechanics. And I'm summarizing this here. In today's terminology, I'm not entirely faithful to the original system and terminology here. The main point is that it is because of von Neumann's work in the 1920s on the foundations of quantum mechanics that we think of quantum mechanics today as non-commutative probability theory. What this means that the classical concept, the concepts of classical probability theory, which are in blue on the left-hand side, are replaced by quantum counterpart. There's a very strong correlation, a very nice analogy between classical and quantum probability theory. Classical probability theory is a triplet, essentially. You have the set of elementary events. You have a certain set of subsets, a set of certain subsets of the set of elementary events, which is a Boolean algebra. In general, it's a sigma field. And the probability measure is a map on that sigma field into the 0-1 interval. That gives you the probability. Random variables, which are defined on the set of elementary events and, say, take values in the set of real numbers, are measurable functions, and there is a particular type of them which is the bounded measurable functions. The quantum counterpart of these concepts, instead of a Boolean algebra, you take the lattice of projections of an abstract Hilbert space. A quantum state will be a generalized probability measure on this projection lattice, and linear operators correspond to random variables and bounded operators to bounded random variables. What did von Neumann do in connection with this picture of what quantum mechanics is? It was him who, in his first paper on the mathematical foundations of quantum mechanics, isolated the notion of abstract Hilbert space. it's really recommended to have a look at that paper. It's a beautiful example of how mathematical generalization takes place by a great mind, having a look at particular representations of a structure and isolating what seems to be common in them and fixing them axiomatically. It's beautiful. It's really beautiful. And I think it's been translated into Hungarian as well. So he created the notion of abstract Hilbert space. Side remark, he also demanded the Hilbert space to be separable, which nowadays is not part of the definition of the Hilbert space. And he started the investigation of the set of projections on an abstract Hilbert space. He also saw that they do not satisfy the distributivity law with respect to the lattice operations, but in the finite dimensional case, they have a weakened form of distributivity, the modularity property, and in the infinite dimensional case, they don't even satisfy that property, but another one, which is a later terminology, orthomodularity. The key ingredient in this analogy is, however, what is called the spectral theorem, which von Neumann proved. This allowed the identification of the linear operators with random variables. You recall that the random variable in a classical probability theory is a random variable because it's a measurable function, which means that the inverse image function is a homomorphism from the Borel set, Borel sigma algebra, into the Boolean algebra, which is the domain of the specification of the probability measure. What von Neumann proved, and this is the content of the spectral theorem, is that linear operators can be identified with homomorphisms from the Borel field into the, not Boolean algebra this time, but the projection lattice. This was quite remarkable because that was the neuralgic point which was missing from the Hilbert von Neumann Norton paper. This is the problem of the eigenvalue problem could not be solved there properly. In terms of the spectral theorem, the eigenvalue problem was solved completely. And this allowed, von Neumann emphasizes this, the treatment of the discrete and the continuous spectrum in a unified manner, and this made quantum mechanics essentially free of mathematical contradictions. So this was the main achievements of the 1920s on the foundations of quantum mechanics. These were summarized in the book published by Springer in 1932, and I'd like to quote now von Neumann, showing you how he himself thought about the nature of this foundational work. He writes the following in a letter to Serker. Serker was the president of Dover Publications, and von Neumann was negotiating the English translation of his originally German Mathematical Foundations of Quantum Mechanics by Dover. Von Neumann writes, "The subject matter is partly physical mathematical, partly, however, a very involved conceptual critique of the logical foundations of various disciplines: theory of probability, thermodynamics, classical mechanics, classical statistical mechanics, quantum mechanics. This philosophical epistemological discussion has to be continuously tied in and quite critically synchronized with the parallel mathematical physical discussion. It is, by the way, one of the essential justifications of the book, which gives it a content not covered in other treatises written by physicists or by mathematicians on quantum mechanics." So von Neumann points out here what he takes to be the unique feature of his work on the mathematical foundations. And this is, in my formulation, this is mathematical physics. It's not mathematics simply, it's not physics simply, it's mathematical physics. And by being mathematical physics, it's very close to philosophy. I hope you forgive me and you don't consider this as a chauvinism on my part when I say the importance of philosophy in connection with this, but this is von Neumann saying explicitly it's to a large extent philosophical. I would even be willing risking being provocative to say that mathematical physics is the technically explicit philosophy of physics. If you press me hard on this, I might back up and say, okay, I don't want to say this, but for the sake of the argument, I might risk this statement. So this work was very philosophical, was very conceptual, was very unique, and it was mathematical physics with philosophical flavor. So quantum mechanics was put into order without mathematical contradictions in 1932. However, there was another period here between 1932 and 1954. Von Neumann writes in a letter to Gerhard Birkhoff in November 1935, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space anymore. What did he believe then? What did he want to replace the beautifully developed Hilbert space formalism of quantum mechanics? This is a very, very long and very technical story. I would like to, again, just summarize what I take to be the main point. In the 1930s, von Neumann started working on the theory of von Neumann, what are called von Neumann algebras today. So instead of replacing classical probabilistic concept with the Hilbert space quantum mechanics, Hilbert space probability theory concepts, he suggests replacing a Boolean algebra not by a von Neumann lattice, not by a Hilbert lattice, but by a von Neumann lattice of projections of a von Neumann algebra. A quantum state should again be a countably additive map on the projection lattice into the 0-1 interval, and linear operators should be again identified with those spectral measures, homomorphisms, which have the feature that their range is in the projection lattice, and the rest is the same. This idea is based crucially on the notion of the von Neumann algebra, which is a subalgebra, star subalgebra of the set of all bounded operators, which has the feature that it is closed with respect to a weaker topology than the uniform operator topology. Von Neumann initiated the study of these algebras in the late 1920s, and he proved the crucial theorem about this, the von Neumann double commutant theorem, which I'm not stating here except to say that it was remarkable and beautiful because it characterized topological closeness in terms of an algebraic property, which is very surprising, I think, for a mathematician. What is the significance of this? So this is a general non-classical probability theory now replacing the Hilbert space formalism. And the significance of this is that just like classical measure theory provides all the types of classical probability measure spaces, the von Neumann algebra theory provides all the types of non-classical, non-commutative probability spaces. And this is via the classification theory of the Murray von Neumann, which was published in 1935. So the significance of this moving beyond the Hilbert space formalism is that we are now having a framework in which all types of non-classical, non-commutative probability spaces are possible, very much like classical measure theory provides all the types of classical probability spaces, all the types of classical measure spaces. They are listed here. I'm not going to go through them. And the slogan is then that von Neumann algebra theory is essentially non-commutative measure theory. So von Neumann should be viewed as the non-commutative Kolmogorov. That's the slogan in terms of which you can understand this work, the second phase of von Neumann's work on quantum theory. But this is not even the end of the story. In retrospect, one can say that at the time when von Neumann was working on this, it was mainly mathematically motivated, but these structures have become totally indispensable in today's mathematical physics. These different quantum probability spaces are absolutely indispensable in describing in a mathematically precise manner quantum systems which have infinite degrees of freedom. It's just not possible to describe them. Typical those systems are the infinite Ising model, the ideal Bose gas, and also relativistic quantum field theory is such that the algebras of observables associated with certain space-time regions are provably such type that they do not fit into the Hilbert space formalism. Okay? So von Neumann created here something in the 1930s which became absolutely indispensable later on, in the late 1950s, early 1960s, and also mathematically the von Neumann algebra theory is extremely deep. This is regarded von Neumann's major contribution to mathematics. The problems which he formulated, which he started working on, led to several Fields medals and Wolf medals. So created a field which is extremely rich, extremely deep, and physically indispensable in physics. How much time do I have? Am I allowed to speak more? Because 5 minutes. Oh, that's a disaster. Let me skip then the next slide, although I think it's very interesting. Let's just talk about von Neumann's war work. And here I'm going to let others speak instead of me. That will be more interesting, I'm quite sure. It's well known that von Neumann contributed to the war effort of the US government in different ways as a consultant. Here are some of the consulting positions which he had, and in particular, he was making major contributions to the Manhattan Project. And I would like now to let Hans Bethe talk about von Neumann's contribution to the Manhattan Project.
Von Neumann took part in most of the crucial stages of the bomb's development and was present at the detonation of the first A-bomb at the Trinity site. Nobel Prize winner Hans Bethe, leader of the Theoretical Physics Division in Los Alamos, 1943 to 1946.
In Los Alamos, in 1943, we had the problem of assembling uranium to make an atomic bomb. Dr. von Neumann was a consultant to the laboratory and visited us about 3 times a year for a week or 2 at a time. There were 2 methods being considered. One was to shoot the parts of the bomb together by a gun, and the other method was the so-called implosion, in which you surround the bomb material by high explosive and then explode this explosive so that the metal of the bomb would assemble in a sphere. In the beginning of the Los Alamos laboratory, only the first method seemed to be possible. It was von Neumann who told us and encouraged us to try the second, and who gave us a lot of information on similar work which had been done under his supervision at the Aberdeen Proving Ground in Maryland, in which shaped charges had been developed. He was very positive that an implosion could be developed, and he told us that this would have added advantages for the assembly which we had not realized. One of the advantages which we had realized was that the implosion would bring the material together much faster and therefore would prevent detonation of the weapon before full assembly. Another advantage which he pointed out was that the implosion might squeeze the material and might thereby increase the efficiency of the weapon. Even after his encouragement, however, we still found it very difficult to assemble the material by implosion. There were experiments made under the leadership of Dr. Kistiakowsky of Harvard to study the explosive method without the uranium being around. And unfortunately, they gave all sorts of irregular shapes. Well, this did not trouble von Neumann at all. He suggested to us that we use something to focus the implosion, focus in a similar way as light is focused by a lens. And this device, in fact, has been called an explosive lens. Afterwards, he designed for us some configuration of explosive lenses which actually worked and which was finally used in the assembly that we used for the first bomb in Trinity and afterwards in Nagasaki.
Very crucial contribution. And after the war, the computer design was in von Neumann's main interest, and he convinced the leadership of the Institute of Advanced Study to be home of the computer development, and this project was carried out successfully between 46 and 52. And here are some pictures, well-known pictures, which were taken in front of the computer. Oppenheimer is there in front of the computer. He was the director of the Institute of Advanced Study. And here, John von Neumann, very proudly standing by his brainchild, in a sense. And here is how Hermann Goldstein describes von Neumann's major contribution to the project.
This machine was the concrete embodiment of von Neumann's very great ideas and contributions which he has made to the electronic computer field. In 1946, Johnny asked me if I would join him at the end of the war in Princeton and help him to carry out in concrete form the ideas which he had been working on in 1944 and 1945. Of course, I jumped at the chance. We rushed to Princeton and got started. The machine that eventuated from that is the one you see here, and it contains essentially those things which the modern computer has in it, although in somewhat primitive form. This machine has stored program concept as its major feature, and that, in fact, is the thing which makes the modern computer revolution possible. The older machines required one to clumsily perform hand pluggings of connections which took hours, indeed days. It meant that programming was an art, in fact a very black art, and furthermore it meant that the total number of instructions one could write were comparatively small. This new concept has been carried so far today that programs are written involving tens of millions of instructions, whereas in those days, of course, nobody dreamed of such complexity, but Johnny's idea made this basically possible. What is the stored program concept? Well, it's the notion that you can describe in a finite number of words, in fact, a fairly small number of words, in a fairly simple language, exactly and unequivocally the description of a problem. And that this description is then translated into binary digits and stored in the memory of the computer exactly as numbers are stored. This was the discovery by Johnny. You may say, what's so remarkable about that? Well, the only thing I can tell you in answer to that is it's just like the wheel. What's so remarkable about the wheel? When you look at it, you can't conceive how anybody would not have known that there was one. Indeed, it must have been that the moment somebody mentioned the wheel or somebody mentioned the stored program, everybody around us obviously knew that this was the way to do it. And in fact, we accepted it immediately. It was not one of these inventions or discoveries which is enormously complicated and few people can understand. It's tremendously simple. It immediately hits a person and he knows that's it. Now, this, I believe, was his great discovery.
Okay, so there are 3 more clips. I wouldn't like to abuse your patience. I would like to show you, however, Louis Strauss' very short video in which he talks about von Neumann as an advisor, significance of him as an advisor. And in the very end, there's a bonus video, very short, in which von Neumann is speaking. So if you allow me that kind of extra time, then I would like to do that. And I skip the video clip in which Oscar Morgenstern talks about his association with John von Neumann. So I'm skipping that. This is the Louis Strauss, chairman of the Atomic Energy Commission, talking about von Neumann as an advisor.
Admiral Louis Strauss, chairman of the Atomic Energy Commission during that period.
I remember one particular incident at Walter Reed Hospital, the Army Hospital here in Washington, when the Defense Department felt that it had to consult him. He was their chief scientific advisor on Air Force matters. And I recall the extraordinary picture of sitting beside the bed of this man in his 40s who had been an immigrant. And there surrounding him were the Secretary of Defense, the Deputy Secretary of Defense, the Secretaries of Air, Army, Navy, and the Chiefs of Staff.
Quite impressive how important he was, how eager people in decisive power, decision power, were to listen to him, to his advice. Quite extraordinary. And finally, after some
At the
picture,
time of his death,
John von
Neumann's peers considered him among the world's greatest living mathematicians. Yet he was virtually unknown to the general public. A year-long search for film material turned up only these excerpts from a 1955 TV program, Youth Wants to Know, in which all that the young participants knew about him was that he was an AEC commissioner and a very polite and patient man.
Bill, did you have a quick question there?
We have been seeing all these mechanical instruments and everything, and how are they educating more people to operate these instruments? Is there enough people to do it? Or
I'm glad that you're asking this question, because it's really a very good one. No, we don't have enough people, and we better do something about it. And I hesitate to say that we better do something about it quickly, but rather we better do something about it both quickly and then continuously. In other words, we need more training in science on all levels, in college, in the high schools, and more training of high school teachers. All along the line will have to accelerate a great deal.
Bill, do you think you might get into that sort of field?
No, sir, I'm sort of interested in law a little bit.
He's a lawyer from Arkansas, Dr. Van. You're not going to be an engineer, huh?
No, do you think that more scholarships would help a whole lot if we had a whole lot more scholarships?
Yes, more scholarships would be very important and would be very helpful. But you must also remember that the scholarships help you only at the end of this process. And that before this, one needs very good training in secondary schools. Otherwise, you may never discover that you have that ability. Also, one needs more training of science teachers for the high schools, because otherwise the high schools never get to that point.
Come on over here,
so it will have to affect a whole lot of things.
I think this advice is even valid today. More teaching, more high school teachers, very well trained ones, especially in the field of sciences and mathematics, would be very much needed. So he's very much alive. His advice was very clever, and we'd better listen. Thank you very much.
Thank you. Thank you for accepting the invitation and this nice presentation on the exciting moment of the von Neumann, and would like to in front of audience to give this Neumann medal for you for this presentation.
Very much appreciated. Thank you very much. Thank you.
Okay, after that we have a break. Let's continue in the 11:15. Okay, thank you.
Úgy szeretnék beszélni, hogy látom.
Ott nem látod?
Jó, ott látom.
Ott látod, ott olvasta ő is egyébként, direkt közelebb vittük, direkt közelebb. Ezzel valahogy jár. audience, and the outside we will keep the timing. I hope it's okay. It's here outside is a good discussion, but who is outside on the laptop? I think waiting for the next presentation. Yeah. Okay. Let's continue. We are continuing the conference that new interesting presentation. In this section, the first presenter is Professor Abraham NEUMANN, who is Professor Emeritus of Mathematics at the Hebrew University, as I know, and he is served as president of the Israel chapter of the Game Theory Society, and has been fellow in the Economic Society as well. And he also held position in the visiting scholar at Cornell University, University of California at Berkeley, and Stanford University. Please, your stage is yours. Thank you.
So it's a great pleasure and honor to speak in a conference of my scientific hero, John von Neumann. The topic is a topic in stochastic game theory, which is called stochastic games, and later it will be clear why I choose this particular topic. And it's always good to start a talk with an outline, because when I talk on the outline, I give highlights of few points that will be mentioned, and usually we are used to the fact that we don't always go all the way to the end, so at least you would know what we are missing. So von Neumann was a founding father of many scientific disciplines. One of them is definitely game theory. Yes. And he basically contributed in three different connecting areas in game theory. Often, nowadays, people are either handling the first or the second or the third. And those three topics were strategic games, which were studied and introduced in von Neumann's paper in 1928. Then cooperative games, which are in the book by von Neumann and Morgenstern, 1944. And another component there is the issue of cooperative strategy games, basically to try to incorporate those two theories together to start from the strategic games, moving to the cooperative game, and then making the analysis of these games. The presentation today is a journey from von Neumann's 1928 paper, which marked the birth of the mathematical theory of games to the development of the modern theory of stochastic game. So obviously, I say the mathematical theory of games, but this mathematical theory of games that he initiated was the foundation of many applicable future works. And if we think of the impact of his work and the follow-up, there are at least 12 people that got the Nobel Prize for work in game theory, in economics, the Nobel Prize in economics. So there are few instances of earlier work that used game theory. One is Cournot, 1938, Zermelo from 1913, which I'll describe explicitly what Zermelo did, and Borel, 1921, which I may mention something, but let's just say that he was trying to do what von Neumann did in his paper 1928, but basically he conjectured that something is false, which von Neumann proved it's correct. So we will focus in this talk only on follow-ups of his work on the minimax theorem from 1928. And in this work, he basically did 3 conceptual and technical contributions. One is defining what is a game. Yes. He knew that people are playing poker, chess, soccer, competition between firms, etc. But to formalize it as a mathematical concept, what is a game? Tell me the story. The story of the game could be highly complicated, but make out of it a simple thing. And then once you get into this fact of what is a game, you understand what it is, you understand what is a strategy in a game. Yes? A strategy of a game is a method of how to play the game. Any instances, what you know, what you don't know, take an action as a function of what evolved so far in the game. And then come a brilliant idea that says the way that we are going to analyze this game is basically we could think a priori what is a strategy. There is a strategy of each player, and if we pick a strategy of each player, then we could follow up and see what will be the outcome of the game. The outcome could be probabilistic because there might be some chance moves, but we could compute it. And then we can model the entire situation as a kind of a simultaneous move game where each player is picking up his strategy. It's worth mentioning that in Borel had this intuition as well, but he has summarized it in only one sentence, and it's not clear, but he didn't define formally what's a game, so obviously the birth of this theorem is von Neumann 1928 paper. So his paper was called On the Theory of Games of Strategy, and it contains 4, just this single paper, I say there are 3 parts of his contribution, 4 fundamental contributions. The first is the description of a game of strategy, including who are the players. We'll see that there could be here some confusion from our intuition as laymen. Second, so this first one described many games like chess, poker, Kriegspiel. Probably you don't know what's Kriegspiel, but it's a very interesting game, strategy game, word playing, and as well as a competition among firms, nations, animals, and the various auction mechanisms. And nowadays auctions take such a large part in the real life days that people don't know that there are auctions in trillions of dollars almost daily. The second is the definition of a strategy of a player in a game. So you describe the game, the formal thing, and then you have to define what is a strategy. The third is the description of the game of strategy as a one-shot simultaneous move game. So you have to think of it as before and. Each one puts in a box his strategy, a referee looks on the strategies and now starts to play and follow the game according to this strategy. The fourth is the minimax theorem. Once you have this formalization, then you have what's called the minimax theorem. The minimax theorem is extremely important in economics, but served also as a mathematical tool to solve few old open problems later in the days. But one has to think of it in a smart way. So I said this is the minimax theorem of von Neumann, this paper, where we will start. Then I'll move to stochastic games. These games were introduced by the first that I mentioned here, Nobel Prize winner, Shapley, in '53, and this was a paper that was communicated to the proceeding of the National Academy of Science by von Neumann. I think it's the first paper that von Neumann communicated in game theory after his work to the proceeding of the National Academy of Science. And I will try to describe what is a stochastic game. In the first part, where I speak about the minimax theorem, I would build the minimax theorem, the story behind the minimax theorem, in a format that will be suitable for my definition of what is a stochastic game. So it will follow similar lines, so it will be easier to follow. Then the first paper of Shapley was proving that the discounted stochastic game, and proved there an existence of a min-max theorem for that particular game. I should say a priori that in the initial theory of von Neumann of the minimax theorem and the development, all the games were finite. So they were eventually finitely many strategies. In this theory of stochastic game, we will see that there are infinitely many strategies, even though the game itself could be described by finitely many parameters. So the finiteness comes from the description of the game, but the strategy themselves becomes infinite strategies. Then I will illustrate examples of stochastic games. These examples will be specially tailored for also for explaining what is the game, and also to explain to mathematicians some of the difficulties that arise in stochastic games. Then I will present a result about the existence of the undiscounted value in stochastic game. So in general, in a stochastic game, the play of the game results in a sequence of payoffs to each player. So the player gets a sequence of payoffs. And the question is, you look on the entire game, what is the payoff of the entire game? So if you look on the payoff of the entire game as a long-run average of the payoffs in the one games, that's called the undiscounted game. And the issue whether there exists a value for this game, a minimax theorem for this game, was open for quite some time and settled eventually by Mertens and myself. Then we will switch to the Nash equilibrium theorem, Nash 51. A theorem, a very short paper, a masterpiece. Nash got the Nobel Prize in economics just essentially for this paper. There is almost no paper in economic theory nowadays that doesn't use the concept of the Nash equilibrium theorem. And if we go back to von Neumann, I didn't meet von Neumann, but I was a good close friend to Nash. And so the story from Nash, when he came with the theorem to von Neumann and he showed him, he said, oh, that's a fixed point generalization of the min-max theorem. So immediately I've seen, when he explained him the result, the proof of the result and what is the meaning, but he didn't formalize that in his own paper studying competitive games. And then we will move, since we have the concept of an equilibrium, we'll describe what is a non-zero-sum stochastic game. So in a zero-sum, in a competitive stochastic game, one player maximizes something, and player two is the adversary who tries to minimize this payoff. And then we will define the undiscounted equilibrium in this type of game. And for the mathematicians in the audience or in the online, in honor of another great Hungarian mathematician, Paul Erdős, who used to pose up open problem and offer prices for this problem. So one of the objectives of this talk is to pose an open problem about undiscounted equilibrium in stochastic game, for which I offered already many years ago a prize, which is a dinner in any restaurant in the world, including transportation, if the solution is positive, and a dinner without transportation if the solution is negative. So you're all invited to work on this thing. And I would say that the initial problem that I posed, the one that I'll pose here, I wouldn't have enough time to describe the general problem, but this is a watered down version, but still I would give these prices for these watered-down versions that I am posing here. And then we will close, if there will be time, to discuss on 3 different theories of stochastic game: the asymptotic, uniform, and robust theories of stochastic game. The asymptotic value, a theory developed initially by Bewley and Kohlberg, which looks on the solution of the game. You have a solution of the game, and you try to see there will be various ways of evaluating streams of payoffs, and you want to see if when the players become more patient and more patient, does the solution converge to a limit? This is the Bewley and Kohlberg result there. The uniform value, which was initiated by the work of Mertens and mine, was not only to show that these values converge, but that there is one single strategy that a player could utilize simultaneously, optimizing simultaneously for all the stochastic games with sufficiently patient players. And the final thing is the robust solution of finite stochastic game that tries to show how, in a family of stochastic game, you could vary your optimization in a continuous way, in a uniformly continuous way. So let's go back to the first part. For Neumann, somebody said here that he lived 52 years in one of the seminars, but my computation is 54, right? I think in one of the lectures there was. So he's the father of game theory, and as I said, is the minimax theorem, the competitive, in 1928, and then the 2 other subjects by von Neumann together with Morgenstern, which I was hoping to hear the quote from Morgenstern on that, so I'll get it privately later, what he said about him on his view. Another important Hungarian-American contributor to this theory is Arsani, who also got the Nobel Prize for his contributions in game theory. So we already mentioned 2. I wouldn't mention all the 12, but we have those 2. And as I remember that this contribution has 3 components: what is a game, what is a strategy, and the minimax theorem. And when we describe what is a game, in particular, what is a player in a game? Okay? So let's look on a few examples of players. Okay, you have at least two great Hungarian chess players, Judith Polgar and Lajos Portis, who are still alive. I think there is one even greater chess player that is no longer alive from the earlier 20th century. And I'll speak in a minute about the work of Zermelo on chess. But a player in chess, in the game of chess, is not one of these players. Yes? A player is the position. You are white, and you look what white in chess could do, the strategies of white. It is true that in game theory there is room to incorporate also the analysis of games in which you incorporate the same game of chess. You look of it as a family of several games with different abilities of the players, and the question is how to formalize what are different abilities of the players and to classify it as a family of games. Another game that I like is soccer. And one of the Hungarian famous players in soccer, probably the greatest of all times, is Puskás. Yes. And again, the game of soccer is also a game, but it's more difficult in a sense to formalize it without taking into account abilities of the players. And as we will formalize other games, that we think of it as sequence of games, so a sequence of stages by which there is one first move, second move, and so on. It's a kind of a game in continuous time, because all the time there are outcomes of actions of the players. So there will be a small reference to continuous time games later, but again, soccer would not be covered by what I'm speaking today. So the first kind of mathematical theorem in game theory was Cermello, that he delivered a talk in the 1912 Congress of Mathematics, and he proved that in the game of chess, either white can force a win, so either white has some strategy, you could write instructions for white that will force that he wins the game, or black can force a win, or each one could force a draw. By the way, it's an interesting question. Nobody knows nowadays, even though there is a feeling that the black can force a win is not possible, because from experience people are used to the fact that white has a slight advantage. But nobody could, so far, nobody can prove it, this theorem, that this possibility that black can force a win is not true. Okay, so I will essentially almost prove you this theorem of Cermello. And I will state a more general theorem, which is a win-loss game of perfect information. So we look on a game, on a result on games that generalizes that Cermello's theorem follows from it. And we look on sequential games. First stage, player 1 chooses a move A1, and thereafter player 2 chooses a move B1. In the kth stage of the game, player 1 chooses AK, and player 2 chooses BK. So now we know what the game is progressing. So a play of the game will be a sequence of moves, A1, B1, up to AN, BN, if it's an end-stage game. And then we define when player 1 wins. So I said a sequential game with perfect information. In a moment, I'll explain the concept of perfect information. And then there are a sequence of moves, plays of game, by which one wins. And otherwise, player 2 wins. The game is of perfect information if before each of his choices of a player, he observes all past moves. So he knows what happened so far. And now comes a concept which is important. The pure strategy of a player in such a game, since he knows everything in the past, is what he does in his kth move as a function of all past moves. And the theorem, the determinacy of games of perfect information without chance moves, here there were no chance moves like in chess. In poker or in other games there would be chance move, that either player 1 has a pure strategy that guarantees that player 1 wins, or player 2 has a strategy that guarantees that 2 wins. And for the mathematicians, you have a trivial proof of this theorem, because it follows from the fact that the logical negation of the formal quantifier statement that player 1 has a winning strategy is the formal quantifier statement that player 2 has a winning strategy. Because what is the formal statement that player 1 has a winning strategy? That there exists a first move, such that for any reply of player 2, there exists a second move of player 1, such that for every, and so on, such that the sequence is a win for player 1. Isn't that set W? What is the negation of this statement, logically? If there doesn't exist a first move for player 1, it means that for every move of player 1, there exists a move of player 2 such that this is not in W. So if you look on it from the logical statement, and for the mathematicians, it's people are making these statements automatically in all their logical arguments, but they never prove it. So you have to prove it by induction. Yes? Okay, now let me give an example of matching pennies, a simultaneous move game, because we say that eventually translate everything to a simultaneous move game. So let's look on one simultaneous move game, which is described by this matrix. Player 1, his strategy are either top or bottom. Player 2 strategies are either left or right. And the entry in the matrix specifies what is the payoff to player 1, namely if he wins or loses. So this is not a game of perfect information, because you don't observe first the move of the other player before you take your move. It's simultaneous moves. And you could see that in this game, if player 1 takes the first move, all that he can guarantee is a payoff of 0. And if player 2 is the first one to take the move, all he guarantees player 1 could force a win. So in symbols, for the mathematicians, I write it here. Yes? The max-min, maximizing over the strategy of player 1, minimizing over the strategy of player 2. The pure strategy, this gives 0. Player 1 cannot force a win. But if you minimize by a strategy of player 2, and then look on the reply of player 1, the min-max is 1. So if player 2 would have moved first, let's look on an end-stage simultaneous move games. Before it was one move. So the first, player 1 chooses A1 and B1 simultaneously. And thereafter, there is a chance move. Chance makes a move C1. The Kate stage, player 1 takes an action AK and BK, and player 2 BK simultaneously, and then nature chooses CK. So the play of the game, first of all, the distribution of CK of nature, when I say nature, means that its distribution is determined by everything that followed so far in the game. It's not a choice of nature, it's dictated by the rules. A play of the game is a sequence of moves of players and nature, and again, player 1 wins if that sequence is in some specific winning strategy. So W is a subset of the place. A place includes here also the moves of nature. And the game is finite if the number of moves at each stage is finite. And von Neumann's result 1928 is that any finite simultaneous move game has a value V, namely player 1 as a mixed strategy. So not a pure strategy as before that he specifies all the rules. He disguises what he takes as his first move. He takes a probability distribution, which is called the mixed strategy, that guarantees that he wins with probability at least V, and player 2 as a mixed strategy that guarantees that player 1 will win with probability at most V, and therefore V is called the minimax value of the game. So this can be generalized to matrix game. So player 1, the pure strategies are a set A, the pure strategies of player 2 are B, and then we have a real valued function as a result of the choice of the two pure actions A and B. And the players, we think of it as playing simultaneously. And one could say that any such game, I wrote a general payoff, but it is equivalent to a win-loss game with a chance moves, because if the payoff is 1/2, you could interpret it as nature decides if the payoff is 1 with probability 1/2 or 0 with probability 1/2. And the minimax theorem of von Neumann states that any finite matrix game has a value V, and each player has an optimal strategy. Namely, there exists a number V, called the minimax value of the game. Player 1 has a mixed strategy, called an optimal strategy, that guarantees that the expectation of his payoff is at least V, no matter what is the strategy of player 2. And player 2 has a mixed strategy called optimal strategy of player 2 that guarantees that the expectation of the payoff of player 1 is at most V, no matter what is the strategy that player 1 takes. Now let's move to the second part, which is stochastic games. And in my description of the simultaneous move games with chance moves were a kind of a preparation for this type of model. So this was a paper by Shapley, 53, communicated by von Neumann. So what is a two-person zero-sum stochastic game? It's a multi-stage game. The environment or position or state, the formal language is state, changes from one stage to the next stage. If you think of fighting, of utilizing natural resources, if you use some of the resources, you affect the situation of next time. If you look on models of global warming, then, and you try to optimize maybe the average of the GNP of the world, you know that if you make too much optimization, you may damage the future time. And therefore, there is a situation that changes from time to time. In each stage, the players face a matrix game. So I'm going back now to the two-person zero-sum, so it's easy to illustrate. So in each state, you think of a matrix game. But the current state and the actions of the players at this stage specify the payoff that the player gets. The stochastic game payoff is a weighted in the entire game. We say you get stages, is a kind of a weighted average of the stage payoffs, or a limit of such weighted, like I said before, the long run average of this payoff. Therefore, in a stochastic game, in all the applications, and also in the mathematical theory of it, the choice of action at each stage is guided by two often conflicting objectives. On the one hand, you want to maximize the payoff that you get today in this period, but on the other hand, you want to guarantee that you are moving to the next state that is favorable for you. A pair of strategies like before of player 1 and player 2 define a probability distribution over place of, and therefore also over the streams of payoffs. And the objective of each player depends on his valuation of the streams of payoffs. Player 1 desires to maximize his valuation of the stream of payoffs, and player 2, who is the adversary of player 1, tries to minimize it. So the minimax theorem for discounted stochastic game. So in the first paper of Shapley, slightly more general, but at least if you look on the game, it generates a sequence of payoff G1 in period 1, G2 in period 2, and so on. And you evaluate the stream as often is classical by economic theories to take the discount, the present value of it, to weigh the different payoffs GT at period T by this weight. The sum of the weights is 1. You always take sum of the weights of 1 so that a constant payoff is valued as this constant payoff. And Shapley's 53 paper shows that any two zero-sum R-discounted stochastic game with finitely many states and actions as a value, which we'll call VR for later notation, and each player has stationary optimal strategies. The fact stationary strategy means that you don't have to look on everything that happened so far in the game. You just have to look on the present situation. And the reason is that if you look on this payoff function, if you know what happened in the first stages, 5 stages of the game, from here onward, you are trying to optimize, again, a multiple of such things. So you can forget the history. I would already right now say that in the long run average, this property of stationary or disregarding the history is impossible. So let me quickly describe to you one such stochastic game. Called the MIG match, was introduced by Gillette in '57 and solved by Blackwell and Ferguson in the late '60s. So I say there are states, and in each state there is a matrix game. So the two bottom one are trivial matrix games, a payoff of 0, a payoff of 1. You could interpret it winning or losing in this period. And the top payoff is, the top matrix is like the matching pennies. But now I have to decide what happens to the transitions. What is the next state? So if we are in each one of those bottom two states, yes, we are basically staying there. There is no move out. These are kind of absorbing states. But if we are on the top matrix, if we play that box, then we move to this state. If we play that box, we move to this space. And if we play the bottom, the top row, we play again this game. How to optimize this if you worry about the long-term averages of the game? Not a trivial issue. It's took a couple of years since the statement of this problem for its solution. In the undiscounted player, one maximizes the frequency of winning rounds, the rounds by which the payoff is 1. I'll show you another game very quickly, which is the Bewley and Colbert game, 1976, which has slightly twist on it. So you see that in this game, you have 4 different matrix games, 4 different positions. In each one, the payoff is specified. So in this game, all the fight will be for the next position, not for the payoff, because you know that in each of these states, you'll get the payoff. In the bottom one, you come back. From these boxes, you are going here from those boxes, you are staying in the same game. From if you play this box or this box, you stay in the same matrix game. And in all other cases, you are switching stages. Again, when they posed it, it was unclear how to play this game. What is the value of this game if you are playing it for infinitely many rounds and you try to maximize the expected rounds that you are winning the game. So strategies in the stochastic games are exactly like strategies in the simultaneous move games with chance moves, because what we have here is simultaneous moves and chance moves. So you have the concept of a play of the game, which is the initial state, the actions of the two players, the next state that nature chooses according to some fixed probability. So this is a play. And a strategy specifies, the player specifies the action as a function of everything that in the past. So we are looking here on case that you remember all the past. So you get a sequence of stage payoffs. And so the solution for the general finite stochastic game is 2-person zero-sum, was in a paper of Mertens and myself that we proved that any 2-person zero-sum undiscounted, so we look on the long-run average stochastic game with finitely many states and action as a value v, namely, and let me elaborate, what does it mean? There is a number v, like in the minimax theorem, and for every epsilon, each player has epsilon optimal strategies. There is no chance here to get optimal strategies. Only you could maximize within an epsilon. And this means that if you take the limit superior, the long-run average, if you want to take the limit inferior, for mathematicians you have to be specific. So look on the limit superior. Player one has a strategy that guarantees that the expectation of this long-run average is at least v minus epsilon, no matter what is the strategy of player two. And similarly, player two has a strategy, a mixed strategy, that guarantees that the expectation of this payoff is no more than v plus epsilon, no matter what the strategy of player one is. And I already indicated before, but let me repeat, it's an important story here. Obviously, if you played 10 periods of the game, all that matters is the future payoffs, because you look on the long-run average. So it looks that if you should have been able to play optimally or approximate optimally without looking back. This is not the case. It's impossible. You must look on the back. And if you remember from the Bible, the paros strategy is if you have 7 years, you will have 7 years with good productivity, be careful, save some for the next years that will be with low probability. So you have to look, your actions is not stationary, is not just time dependent. You look what happened in the past. And indeed, the solution of this theorem was a kind of a similarity to what the Federal Reserve in the US is doing. It's basically adjusting interest rates according to the performance of the economy. So when they see that people are investing too much now, and you think it's too much investment, take care of now, they increase the interest rate. Say, careful, today is more important than tomorrow. And basically the solution of that is a very careful play with interest rates, with a discount factor, that you compute that discount factor as a function of what happened in the past, so like the Faro strategies, and you play optimally as if you are in an R-discounted game. So let's move now to, how much time are you? 8? It's 45, I started 8 minutes, okay. So quickly I want to come to the open problem. So Nash, 1928 to 2015, is the only person who has been awarded both the Nobel Prize in economics and the Abel Prize in mathematics. And obviously, if von Neumann would have lived slightly longer, he will be in the same category. Yes. And as mentioned before, also winning all the Nobel Prizes in a few other areas. So Nash equilibrium theorem, multiplayer, so the same as two players competition. You look on each player as his own pair of functions, so not as before, as one maximizes, the other one minimizes. And a Nash equilibrium is a list of strategies that no player can benefit from unilateral deviation. And the theorem of Nash says that a game with finitely many players and pure strategy has a Nash equilibrium. Namely, there is a list of mixed strategies, X star I for each player, such that if only player I decides to switch, it doesn't gain anything. So no unilateral deviation generates thing. Multiplayer non-zero-sum games is the trivial generalization of the previous two-person competitive game. The state changes from stage to stage. In each stage, the players face a multiplayer non-zero-sum game. The current state and action profile of the players determine the payoff in this stage and the probability distribution to the next stage. A list of strategies of the players define a probability distribution over plays of the stream and over streams of payoffs. And each player desires to maximize his own valuation of the stream of his payoffs. So a play defines a stream of stage payoff. Okay, we could run on that. And let's define what is the undiscounted equilibrium in finite non-zero-sum stochastic game. So the number of players is finite, the number of states is finite, the number of actions of each player is finite. An undiscounted epsilon equilibrium is a strategy profile such that no player can benefit by more than epsilon from a unilateral deviation. Namely, the expectation with respect to this strategy sigma epsilon defines the distribution. The expectation of the limits superior of the averages of his payoff is at least what he will get by some unilateral deviation to a strategy sigma I up to an epsilon for any deviation. An open problem, the one that I promised, the dinner plus transportation, is it true that any finite stochastic game has for every epsilon an undiscounted equilibrium? And there are special cases, much work has been done on this work, and special cases are known that this is true. It's stochastic games with perfect information, which are stochastic games, finite stochastic games, where for each state only one player moves. There are irreducible games, which means if you play a family of what's called stationary strategies, then the Markov chain on the state is irreducible. It is true for two-player stochastic games, a deep result, over 100 pages of proofs by VA. It's true for three-player, a subclass of stochastic game called absorbing games, and several classes of quitting games. And now a comment relating a little to soccer. A stochastic game is a discrete time multi-stage game. So we have stages 1 and 1. The analogous continuous time version of a stochastic game has an undiscounted equilibrium. A priori, it looks a more complicated model, but some new features evolve in the continuous time that you could prove this theorem. And this is a result of mine, that any continuous time finite stochastic game has for every epsilon an undiscounted epsilon equilibrium. And another class of games for which we know that this is the case is finite stochastic game with observable mixed action. When you are coming to a stage, you could choose to play top or bottom, let's say, with probability half and half. But the question is, the other player doesn't know that you chose it with probability half and half. He only observes what you actually chose. So in a stochastic game, you'll try to infer from the other of what are the probabilities. But if you are sending these instructions to a referee who discloses it to the other player, These are stochastic games with observable mixed actions, and a forthcoming result is that any finite stochastic game with observable mixed action, as for every epsilon, an undiscounted epsilon equilibrium. And the results also for classical stochastic game, but now with finitely many states, convex, that's for the mathematicians that are familiar with this concept, convex semi-algebraic action sets and multilinear payoff and transition functions. And I would just finish here with the last slide. The presentation will be on my site, so you can view the details, what is each one of these meanings. These are the three topics that I said. I'm not sure that I'll get to it in the lecture. So there is the asymptotic theory, the uniform theory, and the robust theory, where we look on different concepts. Thank you.
When we started to organize this conference, everyone is saying that we should a presentation on the game theory. This is a very impressive from Neumann, and we are happy to you accepted our invitation and give an outline of game theory, and we see some results from you as well. Thank you very much for the presentation. Is a medal from this memorial year. Thank you very much. Yes, thank you. And we have a new area. We are moving to the new area. The next presenter is Professor Domokos Szász. He is a Széchenyi Prize winner, Hungarian mathematician, and professor of the Budapest University of Technology and Economy, and he is member of the Hungarian Academy as well. And the topic is the Neumann result of the ergodic theorem. Please.
Well, thank you very much for the introduction and for the invitation. It's a great pleasure to talk here. Of course, it's very hard to talk after two excellent talks. So, well, before starting, so this is the content of my talk, and there is a zeros point in that, which is actually before the actual mathematical content of my lecture. It's about the breadth of Neumann's reputation. Recently, this spring, I was drinking beer with a Russian-American mathematician friend of mine, and he said that the greatest mathematician of the 20th century was definitely Neumann. I was modest. I told him, well, there were several excellent mathematicians in the 20th century, but he said, look at Wikipedia. So I looked at Wikipedia, and there is this part in Wikipedia someone is known for. And yellow means the subjects which Neumann is known for. So you can see the start of the list, and there is the continuation of the list, and at the end of this continuation, there is plus 93. Almost infinite. So, okay, I just looked up Einstein. Now there is Einstein in Wikipedia, so this blue, the achievements of Einstein, known for, so on this page and on the next page, not comparable. Of course, there is no sense to compare these giants of science, but that's an interesting remark. Okay, go to the actual content of my talk. Probably I will repeat some points, but that doesn't make any problem. So Neumann was born in 1903, so the father convinced him to study chemistry, so he studied chemistry in Berlin and ETH. During these studies, he made a PhD with Lipót Fejér, Hungarian excellent mathematician, about the axiomatization of set theory. We have heard about it today. Now, in 26, there was a big change in Neumann's life and his scientific interest. So from early autumn in 26, he went to Göttingen. And Göttingen was the center, a boiling center of science, of physics and mathematics. So you see who were there. So there was the birth of quantum theory. There were Heisenberg born. So you see the names. Actually, in italics, you see the names who later received the Nobel Prizes. 7 people received the Nobel Prizes, and probably Oppenheimer and Teller didn't receive the Nobel Prize because of political reasons, but that's not my topic to talk about it. So there was quantum physics in birth. Moreover, and I think this is why actually Neumann went to Göttingen, because Hilbert was there, and Hilbert had an interest in set theory, in logic. And Hilbert appreciated the influence set theory, logic, and Hilbert was also interested in quantum theory, and in general, the neighborhood that year in Göttingen was 23. He was 23. So at this age, he could absorb a lot of new ideas, and he did absorb a lot of new ideas, and he was very much influenced. It's fantastic what he did. So you will see, actually, in earlier talks, you could have already seen what he did, but I will now go to one problem which Hilbert was interested in. So mathematicians certainly know, but non-mathematicians might be interested to learn that. So Hilbert was a sort of leading personality in mathematics at this time. So in 900, there was an International Congress of Mathematicians in Paris, and Hilbert, as a prestigious, most prestigious mathematician, he was asked to talk about some problems for the 20th century. So he collected 23 problems for the 20th century. And among these problems, there was one problem, the sixth problem, which the title is Mathematical Treatment of the Axioms of Physics. And this is the text from the beginning of Hilbert's formulation. The investigations on the foundations of geometry suggest the problem to treat in the same manner by means of axioms those physical sciences in which mathematics play an important part. In the first rank are the theory of probabilities and mechanics. As to the theory of probability, well, just one remark. So, foundations of geometry. We learned at school about Euclidean axioms from geometry. So that was the goal of mathematical theories, to repeat mathematical theories like geometry in Euclid's form. So return to Hilbert's text. As to the axiom of the theory of probabilities, it seems to me desirable that their logical investigation should be accompanied by a rigorous and satisfactory development of the method of mean values in mathematical physics, and in particular in the kinetic theory of gases. So what happened before? What turned Hilbert's interest to this question? Actually, I call your attention that this formulation of the sixth problem is rather vague. And it's not surprising, because mathematics at this time was not sufficiently developed to give a more, mathematics of these subjects was not sufficiently developed to give a more precise formulation, but Hilbert definitely stressed the importance to understand this. So there were some results earlier. For instance, there were very nice, very beautiful results in a sort of naive probability theory, Fermat, Pascal, Bernoulli, Laplace. You see these names earlier, much earlier. I just remarked that the axiomatizations of probability theory only happened in 1933 by Kolmogorov. And the other topic is the birth of naive statistical physics. So in the 19th century, Gibbs, Maxwell, and Boltzmann, they were trying to give some more strict formulation of the theory, of the kinetic theory of gases, for instance. In fact, Boltzmann had several papers about this, and he formulated an ergodic hypothesis, which was in terms of physics, so it was not well formed, it was roughly formed, but it certainly was important, and he formulated the ergodic hypothesis. Okay. Now, I will try to give some idea what had Boltzmann in mind. And I will try to give the simplest example for that. So understand notions like temperature, pressure of a gas. We completely understand. I mean, we think we completely understand what it is. So, but these guys, they wanted to give a better understanding. So, and processes like diffusion, heat transfer, and so on. So, let me focus on pressure. Well, there is, in this picture, you see, I'm not so, what did I do? Okay. No. Can you work? Okay. No, not yet, but I'm not so good as you were in this. So I would like to point to, from...
Point on that. You point on this.
No. Okay. No. Okay, I will avoid it. So in this, this is a two-dimensional picture, and you can imagine it's particles of a gas. Each particle has they have equal masses, and each has a velocity. And you understand what pressure is. You understand that pressure is the following, that on the boundary of the square, how you measure, so you take some average in time in a unit surface, and unit time you take the average, and this is what we think it's a pressure. It's a very simple thing, but to give a precise mathematical explanation or physical explanation for that, it's not so easy, and this I will talk about. This is actually Boltzmann ergodic hypothesis that this pressure really exists, and what the goal is to derive the ergodic hypothesis, which I will tell you later what it is, from the atomic theory of matter from Newton's laws, from deterministic dynamics. Okay. So I will start with two very simple, the simplest mathematical examples before I go to more complicated models. So there is the head or tail. We heard about games. The head or tail is also a game. This is a sort of mathematical model of this game of head or tails. So this you should understand in the following way. On the left-hand side, you see a picture. It's a map of the interval. It's a map of the interval, and the formula for this map of the interval is on the upper right-hand side. It's called Tx. This is a map. And this is 2x if you are in the left, in the interval I0, and 2x minus 1 if in the right interval. Actually, mathematicians would say that it's 2x modulo 1. So this is the map of the interval. And if you take the second iterate of this map of the interval, then you can see on the right-hand picture how you get the iterates of a point x0. You get tx naught, which is x1, x2, tx1, and so on and so on. Now, a very simple fact that the length is invariant under T. What it means? That it means that if you take a small subinterval and you take the preimages, then it has two preimages and of half size, and the sum of the two halves is the same as 1. So it's, this length is invariant. And one can introduce a sort of symbolic dynamics, which is following the trajectory of this point, and for every n, giving note whether it belongs to the left interval or the right interval, and this is epsilon 0 and so on, epsilon n. Now, it's very easy to see that this epsilon 0, epsilon n is a sequence of independent coin tosses, heads or tails. And we know that by the law of large numbers, if to add up all the epsilons until n minus 1 and divide by the number n, this converges to 1/2, of course. So if you take heads or tails for a long time, then approximately half of the tosses will be. And this is the law of large numbers. This is a very simple example. Now I will show you my last example, which is also a simple, a bit more complicated than the previous one. This is, Arnold's cat map. Well, this is a map of the square. So on the left-hand side, you have a picture of 2 times 3 squares. So I'm talking about the left lower square on the left-hand side. And you take an image by this matrix. It's easy to see that the image of this square will be this elongated parallelogram. And you can do the following. You shift each pieces in the other squares back to the original square. So it's easy to see that if you take the blue triangle, you can shift it back to the original square and you get a blue triangle. The same for the yellow one, the same for the green one. Altogether, you get the same square as you started with. This map is called Arnold's cat because Arnold, a Soviet-Russian mathematician, he wanted to illustrate this in a more interesting way. So he put a cat in this square. He considered the image of the cat first in the parallelogram. You see this elongated picture. And then shifting back the pieces to the original square, you get this rightest hand figure. And this is the image of the cat under one iteration of the map. And again, as I told you, the area is invariant under T. So I showed you these 2 examples because they are the simplest examples of a theorem, of ergodic theorem of of Neumann. Now, what Adler and Weiss, also in 67, they found that they could decompose this original square into three, on the picture they are rectangles, the green one, the red one, and the yellow one. Well, when I am talking about rectangles, there is one thing which I want to explain at this point, that these are, of course, rectangles, not as you see them, but if you do the following, you imagine the square in the following way. You glue the opposing sides of the square to each other. Then, of course, you have a square. You have a square. You first turn and glue opposite sides together. You get something like that. And then the whole thing you can turn over again, and you get a swimming ring, right? And this is, mathematicals call it shorter torus. It's a two-dimensional torus. And this is the so instead of the square, you should imagine the geometry of this swimming ring. And on the swimming ring, these are rectangles. Okay. And you can again do the same, that you make the iterates of this map, of the Arnold's cat map, and at every step you make mark to which part of this decomposition the image belongs, and you get again a so-called symbolic dynamics, epsilon 0, epsilon n. Now, this is not independent random variables as it was the case in the head or tail, but this is a so-called stationary Markov chain. Markov chain is not independent things, but random variables, random objects with no memory. So the present only depends on the previous step, but not the earlier history. Okay, and then for this Markov chain, there is also a law of large numbers, and again, the average converges to some value, which is the mean value, the expected value of this thing. Okay. Now, I go to Neumann's problem, and so what I told you, that Birkhoff made a formulation, Boltzmann made a formulation which had no sense, no mathematical, some intuitive physical sense, definitely it had. It was an ingenious hypothesis, but no mathematical sense behind it. Now, in the beginning of the 20th century, ergodic theory dealing with these kinds of problems developed, and very clever people were trying to understand the notion of ergodicity, George Birkhoff, Bernd Kuppen, and André Weil. On the other hand, also in the early 20th century, something different happened, which we have heard already about it. So Hilbert, Schmidt, and Frederick Ries introduced infinite dimensional spaces. So the space which we think of is the Euclidean space, two-dimensional plane or three-dimensional or space. And one can think of 100-dimensional Euclidean spaces, but as these mathematicians introduced, there is also possible to think in terms of infinite dimensional spaces, which are much similar and much different from finite dimensional Euclidean spaces. But these are the Hilbert spaces. And it turned out that Hilbert spaces meant just the perfect mathematical language for quantum physics. And this was what Neumann also understood it. We heard that he had a joint paper also with Hilbert about this. And in fact, in these years, 30, 31, 32, perhaps already 91, 29 starting, he wrote a great book about mathematical foundations of quantum mechanics. So he knew about Hilbert spaces. He understands, and he applied them. Okay, so what happened then? Then he could formulate his ergodic theorem in 32, and I will give the formulation for the simplest case. So you take again a map of the interval, which preserves the length, we call it Lebesgue measure, mathematicians we call it. And this theorem says the following. Well, there is a Hilbert space behind all these things. I think not only mathematicians, but of course physicists, engineers are familiar with Hilbert spaces because you work with spectrum, spectral decomposition. So this is behind all these, there are Hilbert spaces. So you take the space of so-called square integrable functions, and the theorem says that this average, so-called time average of this function exists, and it's this f bar limit, which depends on the point in principle. And also Neumann could add that this limit function is the projection of the original function to the space of t-invariant functions. So those functions which do not change under this map T. For instance, the constant function, if you apply a map to a point, the function is constant, so the constant function is of course invariant. This is just one direction in this space. This is a projection, not in a Euclidean space, but it's an infinite dimensional space. So he could characterize the limit. And then there is a mathematical definition that this map, this transformation is called ergodic if this limit limit is consists of the invariant functions contain only the constant functions. So it's constant functions, constant times a constant is also a constant, so this is a one-dimensional line, actually. So this is the only invariant function, this one. So this is the definition of ergodicity. And very briefly, when I started, can you tell me? 20 minutes. You have 20 minutes. 20 minutes. Thank you very much. I will try to control myself. So now I will give you a one-page proof of Neumann's theorem. So this wants to illustrate what I said in the title, a small step for a genius, because it's really, now we understand it's a simple fact. It's a simple proof. I can give it in roughly one page. So if you have a constant function, if you apply this time average of the constant function, in the limit you get a constant, so no question. Now, if you take functions which are of this form, some function g minus its map, tg, then it's very easy to see that if you take this sum, then g minus tg, tg minus t squared, and so on, this sum contains only two terms. And if you divide by n, which tends to infinity, then the limit is 0. Now, these two kind of functions, the constant function and functions which are of this form, g minus tg, easy mathematics gives that these functions are dense in our favorite Hilbert space, so the theorem is true for every function. So it's simple, right? Now, of course, I leave out some mathematical details, but at this point I want to make a remark that Neumann's ergodic theorem, so this limit can be understood in different ways, and mathematicians are eager to understand all the possible ways of these limits. So Neumann's ergodic theorem was formulated in this Hilbert space, so the claim of the theorem should be understood in this space of square integrable functions. And Neumann's theorem doesn't say that the same limit exists for almost every initial point. Not for every, but for almost every. And this is an additional a different statement. And actually what happened in the history that Neumann already understood his theorem, and Neumann was a sort of, his life was mathematics in a leisurely way. So he lived in mathematics, he wanted to discuss mathematics with everyone, and so he also discussed mathematics with George Birkhoff, telling him his proof of the so-called mean ergodic theorem. This is the Neumann ergodic theorem. And of course, the problem arose whether this kind of for almost every point, is it true? This appeared. And Neumann was doing a lot of things parallelly, so he was certainly writing his book, he was working on game theory, and so on, logic. So he didn't focus so much on trying to prove this. And Birkhoff proved, and there is a history which is written actually in several places, that Birkhoff was the editor of the journal where Neumann wanted to publish his paper, and somehow Birkhoff arranged that his paper first appeared, though Neumann's results was the first. But later, this problem was arranged gentleman-like, so from the side of Birkhoff too. So now we know what the history is, and of course, both are great mathematicians. Okay. Now, so the question arises, what about, so I told you that there is this Neumann's ergodic theorem, and we say that this map is ergodic if the limit function is constant. So now I would ask the first video, this one. So these are 5 disks in 2-dimensional. You should understand it's a gas. And there are 5 particles which collide according to Newton's mechanics. And this is on the torus. So here you see what we mathematicians call torus. So if there is a disk going out on one side, it returns on the other side, and the colors mean the energy of the particle. And so Boltzmann's original conjecture somehow was about the following. If you take a gas of particles, then you can measure pressure on the boundary. Well, the torus has no boundary. I will later go to the case when there is a boundary. But even in this case, you can check the energy which comes to a surface of unit measure on this square from one side, and this would be the pressure. So the question is whether this system is ergodic. And, okay, thank you. And Sinai in 1993 formulated the following hypothesis, that if you take any number of hard walls on any dimensional, 2-dimensional, 3-dimensional, whatever, that this system is ergodic, so pressure exists. It does not happen, the following thing, of course we know it does not happen, but mathematically we have to prove. It could also be that there is a limit, and with half probability, the limit is 2, with half probability, it's 1/2. And this could be, but it is not so, and this is what Sinai's hypothesis was for this model. So N is ergodic. Actually, Sinai in 1963 saw that he can prove it, but when he worked out the proof, it turned out that it was a great result, that he could prove that 2 disks on the 2-dimensional torso system of 2 elastic disks colliding, this is ergodic. And later in 1987, they could extend the results for arbitrary dimensions, but only 2 balls. And the method which Sinai worked out for this, for proving the ergodicity, he started the theory of so-called hyperbolic dynamical systems with singularities. And this method became substantial in the theory of chaos. You know the butterfly effect, so behind the butterfly effect there is this kind of hyperbolic behavior. And I repeat here Arnold's cat, which shows that what is important, that you have this expansion, poor cat. So there is expansion in one side, and because of singularities, it's cut into pieces. So this is the simplest example of a hyperbolic dynamical system with singularities. Of course, there are much more interesting examples. For example, you can have heard about the Lorentz attractor. There is also the same phenomenon, that there is hyperbolicity, this expansion and contraction in the other side. So this is what hyperbolicity is about. I don't have time to talk more about it. Now, Sinai studied for his result in 1970, he introduced the Sinai billiard. It turns out that arbitrary number of balls, it's this kind of billiard. So the dark circles, these are on the torus, dark circles, these are fixed so-called scatterers. And the particle, it's a point particle which moves, hits the scatterer, and according to elastic reflection, it gets collided. So this is the Sinai billiard. And the important observation that arbitrary number of balls on the torus is isomorphic to a Sinai billiard. Now, here you saw, I mentioned the results of Sinai and Chernoff-Sinai, the 2 disks or 2 balls in arbitrary dimensional torus, it's an ergodic system. Now, I told about this isomorphy to a Sinai billiard, but the scatterers in the case of 2 balls are strictly convex, like on the left-hand side. So if you have this wave front, after one collision, it gets strictly convex after one collision. And if you have 3 or more balls, then it does not get strictly convex, but only scattering in one direction, in the other direction it's not. So that's an additional problem, and so Sinai and his school, they could not solve it, and this is what we could treat first, 3 and 4 balls, and then with Nándor-Simányi we could prove that almost the hypothesis of Sinai that n balls on the d-dimensional torus ergodic, typically only. So for almost, we were applying algebraic geometric method. We understood that it's not important, but Nándor-Simányi, for Nándor-Simányi, it took 14 years to get the complete answer to the. Okay, now what about general interactions? not only these hard ball collisions of hard balls, which I mentioned. And I think perhaps my time does not permit to go much further, so I want to finish on this at least. So Kolmogorov, Arnold, and Moser, actually Kolmogorov found the idea and he gave a sort of the idea of the proof, but he didn't work out the complete proof in 54, that if you take other interaction than this hardcore collision of hard balls, of billiard balls, then the system is not ergodic. There are unpleasant initial configurations when you don't get this ergodicity, you don't get the pressure correctly. So after this negative result, now the expectation is that if you have a different interaction, then you have one large ergodic component, which is getting larger and larger as the number of the particles tends to infinity. Now, returning to Birkhoff. Birkhoff wanted to give the proof of ergodicity, and he worked a lot on it in general. We see that the system is not ergodic. So, in a sense, he worked in vain. And this is what, so there is a book by Hirsch about Peter Lex. And computers also serve as laboratories for mathematicians. New mathematical relations can be discovered, and our hypotheses and assumptions can be disproved or found more likely by computations. So this shows how Neumann's interests were coupled, computers and mathematics. Locke mentioned George David Birkhoff's lifetime effort to prove the ergodic hypothesis before computers were available. If Birkhoff had been able to test the hypothesis on a computer, he would have found examples where this is not true. By the way, this morning, when I was coming here, I was trying to look up. I know Peter Lex is a Hungarian-born Abel Prize winner mathematician. He left Hungary at the age of 15, and in 41, and he was very gifted. He also got to Los Alamos, where he met Neumann too, and there was an interview with Locke 10 years ago. And the question was that it's certainly true that for being such a tremendously influential figure in 20th century mathematics, von Neumann isn't remarkably well known today. Actually, I have met some Americans. One of them is a Oscar Prize winner film director, and also a regular contributor to National Geographic and other journals. And I asked him, and he hasn't heard about Neumann, so this is the case, and also other Americans did. Why do you believe this is? Why did von Neumann fail to make as large an impact in the public eye as, say, Albert Einstein or Alan Turing? And Peter Lex answered, it's a mystery to me why von Neumann isn't a household name among educated people. The most powerful brain, father of the modern computer, uncle of the atomic bomb. This is the stuff of legends. And he was a legend in his lifetime among those who knew him. Perhaps an article in the New York Times on some anniversary could start the ball rolling. Well, I think my time is over. I would have talked much more about the influence of the ergodic theorem on science, so on the proof of atomic theory and also relation to Einstein. But I thank you for attention. Definitely, I want to.
Thank you very much for the presentation.
Thank you very much.
Thank you very much. Yes, this picture is on the book of Bhattacharya, who issued a book last year, at the end of the last year, and he visited here and visited the high school of Neumann, and we discussed him, and he said it very similar what Domokos said, that he's made interview with many people in the scientists in the different area, chemical and other, and it is not well known on the Neumann, and they decided to write this book. The title is Man from the Future. I think it's very good book, and it was an intention that the Neumann intellectual life. Describe the Neumann intellectual life, not on the daily life, but really a scientific life, because important to show that the scientists in US and UK and other countries, the Neumann works, and I think this book is very good. We was able to make the Hungarian translation as well. You can find in the bookstore, but as I know, it is very popular in UK, and already this Bhattacharya has a show in the US as well, and I hope that this help in this year to show the Neumann importance for the scientists who's not able to know who is in earlier. Okay, thank you very much. And the next topic is quantum informatics. I think is an important question. What is a relation to the quantum informatics to the Neumann? Our presenter is Sándor Imre, Professor Sándor Imre, who is member of the Hungarian Academy, and he is head of the Department of Network System and Service at the Budapest University of Technology, and is a researcher, senior researcher of the Hungarian National Laboratory of the Quantum Informatics. Please.
Thank you very much. Ladies and gentlemen, when I received this beautiful book at the entrance of the corridor, I opened it randomly, and the following quote confronted me. In the long run, the byproducts of nuclear science, means quantum mechanics, may be more important to the physical sciences than the direct result of initiating new sources of energy. So practically, these byproducts, for example, will be my talk this morning about quantum computing and communications, which is really founded and rooted in the works of John von Neumann. Okay. So, probably you remember that this last weekend was very hot in Hungary, around 31, 32 centigrades. And Saturday afternoon, as I was sitting under the big walnut tree in our garden. This tree was planted by the grandma of my wife. And when I was thinking about my today talk, a Hungarian folk song came into my mind from Transylvania. For the English-speaking audience, I translated. This is a raw translation, and it sounds like this. Sorry, I won't sing it. I only read aloud because my voice is not so skilled. So, this walnut tree was planted here by my grandfather. He did not sit in its shade. He did not eat its fruit. He didn't do it for his own benefit, but for someone else. Therefore, his grandchildren bless his memory. So, of course, we can be regarded as engineers dealing with quantum computing and communications as the byproducts of John von Neumann, but I would rather say that we are the fruits of his walnut tree, because quantum mechanics, which is the basics of this quantum computing and communication topic, is founded and mathematically formalized by John von Neumann. Okay. The main topics of my today's talk will cover the basic rules of quantum mechanics, the nanoworld. I apologize, mathematicians and physicists in this room, because I will approach from the engineering perspective. So please forgive me if I'm not as precise as you mathematicians or physicists. So I will give you an interpretation of the postulates, and I will highlight some consequences. And because we are engineers, we would like to apply what the mathematicians and physicists already discovered. Therefore, I will give you an insight into the world of quantum computers and quantum communication devices, and of course, the applications. As in the introduction, it was highlighted that I am the research director of the Quantum Information National Laboratory of Hungary. This organization organizes the efforts, the quantum technology efforts here in Hungary, and I would like to illustrate the results in the field of quantum computing and communication by the results of the Hungarian teams as well. Okay, so when we are speaking about quantum mechanics, I brought here two quotes, one from Einstein. You are probably familiar with this quote: "God does not play dice with the universe." And there was another interesting, at least for me, interesting quote from Max von Laue, who is also, or who was also a Nobel laureate. He said, when he heard about the final solution for the quantum mechanics, that if that turns out to be true, I will quit physics. And this is the reason why quantum computing and communication had a bit delayed compared to nuclear technology, because the strangeness of quantum mechanics was, I'm convinced that the good approach to handle quantum mechanics is in accordance with the motto of NASA. So the aerodynamically, a bumblebee body is not made to fly. The good thing is that the bee doesn't know it. So we need to apply the quantum mechanics, and we should be or must be convinced that it is a valid description of nature. And as engineers, we need to find how can we utilize quantum mechanics. Here is only a picture about the market actually related to the quantum computing and communications. This is a $30 billion market in 2022, and it has a 20% increase compared to the previous years. And I would like to call your attention that this is a foreign chart, but there is Hungary in the middle in the blue box. So we were mentioned, Hungary, as a player in this world. Okay, but if we would like to go closer to quantum mechanics, it is worth investigating the dimensions of the universe, the distances between the biggest dimensions and the smallest one, and it is interesting where the human being is standing between the largest and the smallest. Okay, I will use, or you can use your nail of your thumb to measure the universe. So my question is that if you put your thumb towards the sky on a starry night, how many stars are covered by your fingernail? Any estimation or guesses? Million? 100 million? Billion? Oh, it's good. Okay, I give the solution. Okay. So you cover 15,000 galaxies, and each galaxy has in average 1 billion stars. So the number of stars, and so somehow the size of the universe can be represented by this huge number. On the other hand, if we go down to the level of the elementary particles, which behave according to the quantum mechanics, this is around or below the nanometer range, then you can use your nail to represent this dimension, because your nails grow 1 nanometer, of course, in average, during 1 second. And where is the human being standing, or are standing? Oh, there is a number at the top of the slide. So the number of stars we already discussed. So this huge number meant or referred only to the stars under your nail of your thumb. But the whole number of stars in the universe is the same number as the grains of sand in the Sahara Desert. Or if you compare the number of atoms within you, is more or less a bit larger than the stars in the universe. So Blaise Pascal formulated a very good answer to the question, where are we standing in the universe? For after all, what is man in nature? And nothing in relation to infinity, all in relation to nothing, a central point between nothing and all, and infinitely far from the understanding either. But we know, thanks to John von Neumann, that we are closer and closer to understanding the nature around us. As I mentioned, I am an electrical engineer, so I am dealing with technology and not pure mathematics or physics. So this is a typical life cycle of an invention. This invention is the steam engine. Roughly 2,000 years ago, Herons constructed his ball, which is based on the steam engine principle somehow. And after 2,000 years, we prepared and developed efficient and more efficient steam engines. On the bottom left picture, there is a steam cylinder of the Titanic. This is a huge monstrum with great efficiency among the steam engines. But when we decided to fly with engines, then we realized that the steam engine, the efficiency of the steam engine is not enough to rise the plane to the air. Therefore, we need to stop, think, and find something new principles which make possible to the engine-based flight. This is the explosive engine. This is the case in computer science or computers. So you are, most of you, I'm sure you are familiar with the Moore's law, which states that the number of transistors, the basic building blocks on a microchip, doubles about every 2 years. Similarly, the cost of the computer is halved. But the principle behind this observation is that we design and implement smaller and smaller transistors. Therefore, we can use more and more transistors. Therefore, we can be faster and faster. But there is another consequence of the Moore's law, namely, if we count the electrons per device, the electrons per transistors, when we design smaller and smaller transistors, we will reach the region when only 1 electron will be contained by the transistor. And in this case, one thing is sure, that the transistor works differently as we expected. And this is the range about I am speaking. This is the nanometer or smaller scale, where the quantum mechanics, described by many scientists, but among them John von Neumann also played an important role. So this quantum mechanics describes the rules of how the nature behaves at this scale. Practically, there is only 4 postulates. It depends on, the engineers are saying 4 postulates, physicists sometimes mention 5, but the important thing is that there are several very simple rules for the quantum mechanics. The question is, why do we learn Newtonian physics in the primary school instead of quantum mechanics? The reason is because these rules are quite strange and seem to contradict to the human logic sometimes. So we will go through these basic rules, these postulates from engineering point of view. You are familiar with the phenomenon of classical bit. This is an information containing unit. It can have two logical values, either 0 or 1. I brought here a demonstration device, a 100-forint coin. So it has a head and tail, and it can be regarded as a logical 0 or 1. And on the right-hand side of the slide, you can see a picture of Claude Shannon, who formulated the basics of information theory and defined the so-called Shannon entropy. This is related somehow to the information content of a classical register or a classical bit. Compared to the classical bit, a quantum bit can be regarded as a flipping coin in the air, which contains or carries both values at the same time. So you can realize the difference between the mathematicians and engineers, because Professor NEUMANN and Professor Sass were able to imagine a coin and the two sides, head and tail, without a real coin, but electrical engineers, we always need something to hold in your hands, and we are convinced only if really flips in the air. So practically, the first postulate of quantum mechanics formulates or says that a quantum bit can carry two different classical values at the same time. And if we take the second postulate, we can turn to the chess. Both mathematician professors mentioned chess as an important part of the game theory, but it is important from quantum computing as well, because probably you are familiar with the story of the invention of chess. So when the wise man went to the Shah that he's invented the chess, the Shah was really satisfied and asked him what price he would like to get for the chess. And he said that please put one piece of grain on the first field of the chess table, twice as much, 2 pieces of grain on the second, and he would like to only get the grains on the last field of the chess table. I counted here the top blue number is the number of grains on the last field of the chess table, and this is roughly 70 billion tons of grains, which is the price of this invention. And the EU production is only 210 million again. So what I would like to emphasize, that this exponential calculation or behavior which appears even in the quantum mechanics is very important from computing point of view, because we can store 2 values in 1 quantum bit, we can store 4 in 2 quantum bits, and if we consider only 500 quantum bits, 500 electrons or 500 photons, it will contain more numbers than the number of atoms in the whole universe. So it suggests that somehow we will be able to store information in a very comprised manner, but not as comprised as you think, because there are some randomness in the quantum mechanics. But anyway, this is a good start to build quantum computers. There is another consequences of merging quantum bits into quantum registers. Enrico Fermi said that it is worth making experiments because there are 2 possible outcomes. Either the result of the measurement confirms the theory or the hypothesis, then we are satisfied that we have a good theory. Or contrary, if the result is contrary to the hypothesis, then we made a discovery and we can follow the new tracks. So let me make a thought experiment. Let me consider two coins. First, we consider them classically. If we have two coins and we flip both coins into the air and let them fall, then we will have four different final state of the system, either 0, 0, 0, 1, 1, 0, 1, 1. Compared to this, quantum mechanically, a 2-qubit quantum register may contain these four states at the same time. Within the blue box, there is the quantum description of a 2-qubit register, which tells that the 0, 0, 0, 1, 1, 0, and 1, 1, all these four numbers are stored within the 2-qubit system. But what if we did it two of these four numbers, and we use only the ket 0, 0 and the ket 1, 1, so the classical 0, 0 and the classical 1, 1 value. This can be modeled by a stick which connects or glues the two coins, and the coins are rotating together in a synchronized ways. In that case, we have two possible outcomes, either 0, 0 or 1, 1. Okay, if we do this experiment by two quantum bits, for example, 2 electrons, then the result will be different. I explain you this experiment in the following way. We ask Alice, I don't know whether there is Alice in the room or not, but we ask Alice, thank you. So we have a realize. So we ask her to take one of the quantum bits, one of the 2 electrons, and travel to Sydney to the Opera House, and we ask Bob to take the other quantum bits and travel to New York to the Metropolitan. And exactly at noon, we ask Alice to measure, to check what is the value of his quantum bit, and she can either measure or look 0 or 1, because both values are stored in this composite system. But if Alice measured 0, because the system, the joint system, has only 2 possible joint states, 0, 0 or 1, 1. So if Alice measured 0, then we can be sure that Bob will measure 0, 2. If Alice measured 1, then we can be sure that Bob will measure 1, 2. And this will happen even in the case when the time difference between the 2 measurements is so small that even the light cannot travel between the 2 locations. So it seems to me that there is an effect which is faster than light. We learned from the relativity theory that the speed of light is an upper limit, but speaking correctly, it is valid for the information delivery, and in this case there is no information which travels between the 2 points. But this special phenomenon called entanglement, because the 2 particles, although they are moved in distant places, are in a very strong connection. If we get 0 on one place, the other place, on the other place, there will be 0, 2, and similarly with the ones. How can such strange states generated? This is an entanglement generator from the Quantum Information National Laboratory used for free space quantum communications. So on the bottom left, you can see a laser device. The laser beam goes to a special crystal, a lithium niobate crystal, and there are 2 beams of photons coming out from these crystals, and these photons are entangled. These photons are in special state regarding the polarization. Considering entanglement, it is very interesting and important that if the entanglement is unwanted, so it's generated by the nature, then this is the main bottleneck of quantum computers. Because you can imagine that I have a quantum computer, and within this computer there is an electron whose spin is entangled with another electron in a butterfly flying outside of the Academy of Sciences. And if we measure the butterfly, then it will influence the operation of my computer. So this is a real problem and a real challenge. On the other side, all the actually known quantum algorithms, which are more efficient than the classical counterparts, they are using entanglement, but intentionally generated entanglement. So entanglement is a very important resource in quantum computing and communications. So the third postulate describes how the time evolution of quantum systems work. Practically, we can model them similar to the classical digital technologies where we use elementary XOR, inverter, or other gates. A similar description exists for the quantum world, where we can use, of course, special quantum gates to describe any operation on the quantum bits. And because these quantum bits can be described according to von Neumann by unit-length vector, therefore, we can visualize the operation of a quantum computer by means of a rotation on the surface of a sphere which has unit radius. Okay, sorry. The last and fourth postulate is the so-called measurement or quantum to classic converter. Unfortunately, during the last several million years of evolution, the human race did not develop any senses for the nanoworld. So no one had the opportunity to see an electron or a photon. We try to measure them. We have some information about these elementary particles, but we are not really familiar with its original nature. Therefore, the measurement is very important because it helps us to get information from the quantum level of the systems. Practically, this can be modeled when this coin is flipping in the air. I hit the coin, it will fall down, and either it shows the tail or head. So this is practically a measurement. And there is a famous thought experiment, probably you heard about that. This is the so-called Schrödinger cat paradox, which is nothing else than if we have a quantum world all around, so especially myself, I am consist of plenty of quantum bits. So I can be described by means of a very huge quantum register, of course. But our experience is that if we go or step out from this level of quantum region towards the classical world, towards the size of a human, this quantum behavior, these quantum properties somehow disappears, and this Schrödinger cat's paradoxon somehow tries to explain this strangeness. And even John von Neumann was really interested because this is somehow related to the philosophy, when and how change we from quantum to classical. So therefore, he has results on quantum measurement, how to describe or how to design measurement in quantum system. And this type of measurement is called or named after von Neumann as von Neumann measurement, and we teach this measurement technique for students at the university. Okay, so altogether, I listed here the postulates of quantum mechanics in engineering context and listed the formulas, so there are mathematical formulation behind these postulates. Now I would like to give you a short history, not quantum mechanics, but for the quantum computing and communications. Okay, the starting point in my presentation is the 5th Solvay conference. This is a This was a conference where scientists were collected, especially physicists, who were dealing with the quantum mechanics and try to finalize and formalize the rules of the nature in the quantum regime. And parallelly, there was another big effort to describe the large dimension of the universe. How many Nobel laureates did we use to invent or discover the rules of the large distances? Okay. One or half, because Einstein was the person who, but he received the Nobel prize not for the relativity theory, but the photoelectric effects. On this picture, on the top left, so these are the conference participants. There are 15 Nobel laureates who were worked or related somehow to this quantum mechanics. So you can imagine that the intellectual effort which was needed to finalize and describe the nature at this low level. Thanks to John von Neumann, his book was mentioned before, there was a strict mathematical formulation of quantum mechanics, and Richard Feynman, who was also a Nobel laureate physicist, was the one who published the paper, and he mentioned that maybe it is the time that not only physicists work with the elementary particles, but maybe engineers can think of how to use them for computing. And this was the start of the quest for the quantum computers. There were many ideas how to build or what type of physical objects could be good quantum bits, but it took plenty of time to find appropriate solutions. But in the meantime, mathematicians, engineers were thinking of how to apply, how to use later if we will have real quantum computers. And many algorithms and protocols were born during this period. And even we realized that there is an algorithm called the Shor algorithm, which is able to crack the widely used RSA and public key type of security systems. Therefore, a new track had been initiated, which is the quantum communications. So how can we communicate in a secure way so that even a quantum computer cannot break this code? So one track is this quantum communication. Actually, there are two segments. One is an optical fiber with ground segments or terrestrial segments of quantum communication, and the other is the satellite-based free space segment. And around 2018, some computers were published or were accessible, which we believed that they are more or less really operating in the quantum regime. However, there are true texts even nowadays. One is the quest for the universal quantum computers, which can be programmed to any problem and can solve it very efficiently. And the other track is to develop quantum computers for specific problems. And it is a good question from engineering point of view. What type of programming languages are good enough so that the human logic, which is which were strengthened on in the classical world, so how can this logic translate it to the quantum world, which has a bit different system of rules? And similar to the classical info communication, where you realize that a mobile phone is a computer stronger than the computer which was used to land on the moon. So this is a very serious computer. On the other hand, this is a communication device. So computing and communications integrating during the last several decades. And we expect that in a similar way, quantum computers will be connected so that to generate a higher impact than single standalone computers. The European Union realized that a centralized effort is needed in Europe to be compatible or compatible with the US or the Asian countries. Therefore, in 2016, manifesto, a so-called manifesto, were published, which described 6 areas of quantum technology, and among these areas there is the quantum computers, the intercity quantum link, the satellite link, and the optical fiber-based quantum internet. Practically there are 4 directions, merging directions: communication, computation, simulation of quantum systems, and sensing as well. And taking into account that my time is limited, I brought you only one quantum algorithm to show the efficiency of the quantum computers, and this is related to this not machine learning, to searching and database handling. Okay. You are familiar with the fact that we are collecting information every second. Terabytes of information are collected from the shops, from the communication network, and whatsoever. But this information is useful if we can process this information. And one important problem is the searching, to find a certain element in a very huge database. This problem is as old as the human race, because practically the Stone Age people, when they would like to find something to eat, they had to go to the nature, and the nature is practically an unsorted database. They spend plenty of time to find berries and animals. Is anyone who knows what is the solution of this problem? How did the Stone Age people improve the efficiency? Sorry? Yes, but I have a more general answer. This is agriculture and animal husbandry, because if you need a sheep, go to the shepherd. If you need an apple, go to the apple garden. And if you need a car, go to the garage, and so on. So practically, from computer science point of view, agriculture and animal husbandry means sorting the database. And for the past 10 millennia, we did the same. We always sort. Maybe you have the experience when you visit a large shopping mall or a hypermarket. After several visits, you find the bread, the milk, and what you would like to get. But next time to go to the shop, suddenly this sorted in your mind database becomes unsorted, because the guys who run this shopping mall moved to different locations the goods. Therefore, you need to spend more time. They decrease your efficiency to find the goods in the shopping mall. So they make the database unsorted. Fortunately, there is a quantum algorithm which is able to find a certain element in an unsorted database. So there is no need for sorting. This is called the Grover algorithm. Here you can see on the left-hand side this block diagram of this algorithm, or this we call it Grover operator. On the right-hand side, it shows that this is practically nothing else than rotating the index vector of the database to the appropriate position, and the efficiency of this algorithm scales with the square root of the size of the database. However, from engineering point of view, the finding an element is important, but not so important. What is important to finding the smallest or the largest element in a database? Because typically we engineers optimize so-called goal functions, and we would like to find the optimum solution for a problem. Therefore, this is a result from this Quantum Information National Lab. We had a modified algorithm called quantum existence testing, which is able to decide very efficiently whether a certain element is contained by the database or not. And if we combine this quantum algorithm, this quantum existence testing, with classical logarithmic search, which itself is very efficient for sorted databases, then in that case, here there's an animation how it works. So we can find very quickly the smallest value in the database. So this is I'm saying as a beautiful result because we had a very quick classical algorithm, but it is not able to be used on unsorted databases, but involving a quantum solution and combining them, we can provide a quantum-assisted solution to this problem. Okay. Here, with my PhD student, made some calculations or tested the efficiency of this algorithm. Probably you know that actually nowadays big server farms are used to collect the data and run different processes. So they collect the information, the data from all over the world, make the processing and send back the information or the results. And on this figure, you can see the blue one represents a classical solution, and the red one is the quantum-assisted solution to this problem. If you are interested how to imagine a quantum bit, there are several promising solutions. One could be the usage of the spin of an electron. This is a magnetic property. So an electromagnetic field, by means of an electromagnetic field, we can set up the quantum bit in a superposition state. So it can contain an upwards and downwards state of the spin at the same time. The problem of this approach is that it is very sensitive for the environmental noise, and practically we would like to build several thousand qubit long or large quantum processors. Therefore, it seems that this type of approach is good for proving the concept, but not good for the everyday use. Another possibility, the so-called Cooper pairs, the superconducting electron pairs, they are very good or appropriate solution to store quantum information. The only requirement is that the device has to be cooled down near to 0 Kelvin. So the device itself is like a melon, and everything which provides this, the frigator is like a room. Okay, another possible solution is the ion trap, where ions are stored or carried again in electromagnetic field, and the energy level of these ions carries the quantum information. And the last but not least solution is the photonic quantum computers. These are very promising and as a new approach because photons are very resistive against entanglement, so they are very solid and good quantum bits. The only problem that photons travel with the speed of light, so it is hard to keep them in a certain location. And here there is a figure about the different potential technologies of quantum computers, and I put this yellow dashed line. This is the Moore's law in the quantum regime. It is called Rowe's law because after another scientist. But you can observe that there are certain technologies which may probably continue the Moore's law for quantum computers as well. Of course, there are so-called sure bet technologies. Probably they will be the winner of this competition, but we are not sure. There are several ones which are risky or less reliable. I take among them one, which is this is the IBM's quantum computer. I prefer it from educational point of view because they made publicly available of the small qubit quantum processor. So even undergraduate students from the university can write codes and programs on the processor, send to the cloud, and they run this code on this processor. So you can follow here the different dates and the different numbers of qubits. This is an exponential increase in the number of qubits. Of course, these are the so-called classical qubits, and the really useful operational qubits, which can be used for computation, its number is smaller. So, but we think that Moore's law is still alive in the quantum regime. And here, I would like to only highlight how many companies, different companies, are working on quantum computing, different aspects, of course, computers, programming, applications, and so on. From computer science point of view, if you would like to write a quantum algorithm, which is more efficient than the classical counterparts, more or less it seems to be easy, because every quantum algorithm contains an initialization which can be written in several rows in a program, so it is a very clear and easy job. To define the parallel computation of the quantum computers, it is more or less easy. So after some practicing, you can do this. You can construct measurement thanks to von Neumann, and sometimes we need post-processing to evaluate or understand the results. But the really challenge is the so-called amplitude amplification, which makes the originally inherent randomness in the quantum regime more or less deterministic. So it influences or modifies the probabilities in the quantum regime, so that if we make a measurement, the appropriate answer will be get. And here is an example from Microsoft. This is Q-sharp for a quantum code, and this is the IBM's Qiskit, which is a Python-based quantum programming language. And some results and interesting about quantum communications. The most famous communication protocol is teleportation, not because we would like to teleport anyone in this room or later in the future, but from information theory point of view, the teleportation is nothing else than an entanglement assisted. This means that we use entangled quantum bits for assist the communication. So this is an entanglement assisted transmission of quantum states over classical channels. So it makes it possible that we use classical commercial optical fibers to deliver quantum information. So it is the real importance of the teleportation. And as I mentioned earlier, so the aim of quantum communication is to connect quantum computers and sensors in a large network. And the so-called killer application, the first application which is actually under spreading all around the world, is the so-called quantum key distribution. This is the Gartner hype curve. Quantum key distribution means that we encode classical information into non-orthogonal quantum bits, and thanks to this encoding, if anyone tries to get information from the channel, we can reveal this eavesdropping event. The other, the other item on this curve is the post-quantum cryptography. This means classical efforts to find such classical ciphering algorithms which are resistive against the quantum computers. But because we don't know what are the limitations of a quantum computer, we cannot say that the algorithm really resistive against the quantum attack. Okay. Here is an optical fiber which is used for terrestrial quantum communications. For the sake of comparison, this diagonal black strip is a hair, a strand of hair, and the red one is the core. This is the real part of that, so the optical part of the cable which is used, and we send photons into this small optical or narrow optical cables, not as a bunch of photons as in classical communications, but one by one, and modify the polarization of the photons one by one, and this carries the information. The other segment, as I mentioned, the satellite segment, this is a Chinese satellite. It was launched 2 years ago and made a connection between Graz in Austria and a city in China, and demonstrated that quantum information can be delivered by these 2 distant points. ESA, the European Space Agency, plans to launch the European quantum-capable satellites within 3 or 4 years, and we plan to deploy a receiver station here in Hungary. This is the Hungarian results. Last year, we deployed a testbed in Budapest. It had on the right-hand side, a free space optical link between the building of the Budapest University of Technology and the opposite side of the Danube. There is a building of Vodafone. So it was roughly a 1 kilometer long free space optical communication test, and the other was towards the Wigner Institute of Physics in Csillebérc. This is roughly 10 kilometers, but we use the commercial cable, optical cable of the Hungarian Telecom. So, and this is 2 devices of the fiber-based quantum communication system. These were developed at the Department of at the Faculty of Electrical Engineering and Informatics, together with the colleagues from Wigner and the Faculty of Natural Sciences at the Budapest Institute of Technology. And what we are doing now, we are working on the Hungarian backbone of a quantum network. We are good progress towards Pozsony, Bratislava, and Vienna, Bécs, and there are several other directions toward Pécs, Szeged, and maybe Miskolc, so that big Hungarian cities will be connected by means of quantum devices. This is supported partly by the European Union, partly by the Hungarian government, and next year there will be a call for the cross-connection of the national networks in order to implement a pan-European quantum communication network. So, as a summary, I presented you that we started as engineers roughly after 1930, when the postulates and description of quantum mechanics had been formulated. John von Neumann had important role in this formalization, especially according to the mathematic description of the quantum postulates and operation. But the real work with the elementary particles from engineering point of view started around 1990. In 2010 is the year of the first successful communication experience. 15 is the commercial quantum communication devices, and around 22 there are quantum computers. I wrote here mainframe, similar to the classical big computers, which has distant access and can run difficult problems. And the novelties are the small case quantum networks, which will be later interconnected. And I started with the walnut tree of John von Neumann, and I would like to finish my talk also with him. Every last lecture of my courses on quantum technology is held in the nature. There is a statue of von Neumann roughly 200 meters away from our building. We go there with the students, and I tell them the story of quantum mechanics and quantum technology, and I highlight the Hungarian participants of this process, among them, of course, John von Neumann. So thank you very much for your audience.
Thank you very much for presentation. We learned from Professor Rédei presentation Neumann has two sides. One is a mathematician, other the engineering, and it was important your presentation because they show the engineering heritage of the von Neumann. Thank you very much for the presentation.
Thank you very much. Okay. Thank you.
Okay, after this information-heavy section, we have a lunch break. The lunch will be downstairs in the room Kodai, and we will continue about 2:10. Yes, 14:10. Yeah. not easy to continue after the lunch. Some people is collecting coffee or something like that, but they are joining. I hope that we should continue because some guy looking for us in the YouTube streaming. Therefore, we should continue. We have in the afternoon session 3 presentations. Continuing the John von Neumann life and work explanation. The first presenter afternoon is David Allen Greer, who is a writer, author, and fellow in the Eliot School in Washington.
George Washington
University DC. Yes, and his topic and John von Neumann and his fields. Yes.
Thank you very much. I'm very pleased to be here, very grateful to have been invited. I've chosen a title that's difficult to pronounce, John von Neumann and the Avaricious Field. What I wish to do is help you get a little better understanding of how he worked, of the environment that shaped his thinking. Because without that kind of understanding, it's very easy to think of him as we think of many of the Hungarians who ended up in the United States as aliens from outer space who are just geniuses. There's a process, and there's a process that gives us an insight not only into how he worked, but into how the fields in which he worked developed. So my world is largely the world of computing. I explained to people that I arrived a little bit late for the conference because my plane was hit by a lightning strike and I had to spend the extra night in Zurich. But I'm a mathematician and I don't believe in physical reality. So it was a mathematical lightning strike that had mathematical consequences, which are computational. This is a well-known picture of von Neumann in front of his computer, the Institute for Advanced Study computer. And we're going to work out from that experience and try to understand what he contributed and how he developed his ideas. I'm giving just one part of what's a very big and a very rich and complex story. These are some of the things that von Neumann contributed to and contributed major works to. Computing, which is central for me, is only one part of them. And the picture, again, a well-known picture of von Neumann. Von Neumann, Oppenheimer of the atomic bomb fame, Hermann Goldstein, one of the developers of the computer, and Julian Bigelow, who was one of his engineers, sort of helped give a sense of the world in which he lived in and the kinds of people he worked with and how different they could be. But the picture I'm really going to start with takes us on a different kind of journey. It's a journey that goes from here. This is a woman working in a clothing mill, to here. This is, again, a well-known picture, which is one of my favorites for a deeply personal reason. The woman is Lois Lurgens. She's working at the Maniac, which is a copy, modified copy, of von Neumann's first machine. It's at Los Alamos Laboratories, and her daughter, whose name was Lois, that's Lois Lurgens, her daughter is Susan Lurgens. Susan Lurgens was on my PhD committee. So I have a deep connection to that picture. But we're going to go from one to the other, from one kind of factory to a computer room, or more accurately, from a computing office, which looks something like this, to, again, the IAS machine, the kind of mechanized computing we all know and understand. And if we're going to just finish this off and do it in an abstract way, from massed human labor in human organizations, represented by this chart, to the von Neumann computing architecture. And in case any of you need a quick refresher on the von Neumann architecture, I wasn't sure how many physicists I would be dealing with who say it's just an artifact and not to worry about it. It's useful, as this talk goes on, to remember that he conceived of the computer as a collection of 3 elements. They were a control device, an arithmetic device, and a memory device. The arithmetic device could perform in his model the 4 arithmetic operations: addition, subtraction, multiply, and divide.
The control device would tell the arithmetic device what to do and when to do it and what data to get and where to put the data. The memory would store the data, but it would also store the instructions for the control unit, the program. And that program was a series of instructions represented by numbers, indistinguishable from data, and it would be processed top to bottom, first to last, with jumps. He initially conceived it as jumps backwards, a looping kind of operation, but also grasped very early that there were decisions and other options going on that would cause jumps forward. But that's the structure that is attributed to his name and is very much part of the world that he shaped in the late 1940s and early 1950s. And the question that we have to sort of answer here is not only how he got there, but what's the field that he created? I was president of the IEEE Computer Society. Jim Keller is now president of one of our sister organizations. And I'm sure he will tell you too that the easiest way to get into a fight there is to walk into some meeting and say, computer science really isn't a science, is it? And it really doesn't engineer anything. A fight ensues and it goes on. Computer science as we know it is an avaricious field. It has taken ideas from dozens and dozens of other pieces of intellectual activity and made them its own. If you look at this list, which is by no means complete, we start with numerical analysis and electrical engineering. For a decade, those two fields fought over who was going to own computing. The IEEE in America, the Institute of Electrical and Electronic Engineers, its members largely built the first computers, so it assumed naturally that it owned them, and they could say what computing was and wasn't. The mathematicians used them, and I come more from that standpoint, and believe that hardware is a figment of the imagination created by engineers to keep themselves busy, and they believed that they owned them. And that fight went on until other things started joining. In particular, very quickly in the 1950s, logic, switching theory, psychology as a foundation for artificial intelligence, system engineering, all of this were pulled into computer science in different ways. And that started to shape a new field. In the 60s and 70s, we get economics, management. We get game theory, another von Neumann's great contributions, statistics, quality assurance. All of these things reformulated and reshaped it. And again, this is far from everything. But there's one thing that we as computer scientists often overlook that has had tremendous impact, and we kind of ignore it, and that is factory operation, factory management. In fact, the management of factories was deeply in the thought of the early computer scientists. They took words from it, they took concepts from it, they turned to the thinkers of that field. In particular, we teach kids to program. Every child should learn to program. Comes from what engineers did in a factory. They set up the day's program. They put together a program for the month. Flowcharts, same source. So what does this tell us about von Neumann? And the path we go through is through his computing assistants before he had machines. There are two kinds of assistants. The one which I think is more commonly known and understood were wives, daughters, and students. They were people who were largely unable to have a professional status because of social barriers. Gender was a big one. It's not surprising that the word sons does not appear on that list. And they worked because it was a way for them to contribute, a way for them to be part of the scientist's work, a way for them to have any position at all. The computer there is a woman a little bit later than the numbers on the left suggest. World War I. She was just breaking out, had finished a degree in mathematics, and discovered that that was about the only job she could get. My grandmother had the same experience at about the same time. And the computing sheet is an earlier one, it's from 1799, and we will get to that one in a little bit. Von Neumann had a great variety of computing assistants that we know of. The most common ones were new PhDs. Edward Lorch has very fortunately given us an article, a very extended, detailed article about what he did for von Neumann. And it's clear that he did everything from take notes Okay. Extra little voice here, and we will move on. Edward Lorch would sit in meetings like this one and take notes, and he had no iPhone to do it for him. He had to do it with pen and paper. He would complete von Neumann's articles. He would do von Neumann's calculations. He did a lot for von Neumann, included more or less keeping his office straight. Von Neumann's wife, Clara Dunn, did a lot for him as well. In fact, there have been rightly some questions about what she contributed to him. Clearly, she had some ability of her own that deserves to be recognized more than it is. But she did calculations. She did work writing articles. She did clearly some conceptual things as well. And then there were roughly 6 to 8 young women who were employees of Princeton University who did calculations or programming work after the 50s for von Neumann. Names I have, their histories are vague, the Princeton records are not clear, and of course these weren't students because at the time Princeton was all male. That's the common picture. And if we stick to that, there's not a lot of influence we can trace other than the Edgar Lorch and his crowd. The group that becomes interesting, though, are the organized computing offices that existed in the 1930s and 40s. Actually, they go back to the 18th century. These offices would employ multiple human beings working together in an organized way that divided large, complex problems into small steps. The one that had the greatest, it's hard to say greatest, but one had a great deal of influence on von Neumann was the Math Tables Project, which operated from 38 to 48. But there were others that employed large numbers of people. The Math Tables Project involved 450. Several were smaller, and we will get to them in a moment. It was, however, the largest computing group of its era. The mathematical leader was a woman named Gertrude Blanche. She was the 35th woman in the United States to get a PhD in mathematics. It was the major computing office of World War II for both the United States and Great Britain. 28 volumes of tables, hundreds and hundreds of calculations. Hans Bethe was a champion of the group. Phil Morse, engineer from MIT, did everything he could to support them. The Army, the Navy, the MIT Radiation Laboratory, the Manhattan Project. They did work for ballistics, radar, navigation. This was the largest computing organization the world had ever seen until we got machines. And it did so as a work relief project. You could only get a job there if you had been turned down for jobs at other places. They reduced all calculations down to elementary operations. They had 4 divisions. The addition group was the largest. It was about 60%. Then they had the subtraction group, which was about 20%. And then they had the multiplication group, 1 digit versus a multi-digit number. And then there were the few, the small, the proud, the long dividers. And they worked very hard to make sure that the methods that they used would have limited number of divisions. And particularly, they liked continued fractions, which did that. Now, the history of these groups is actually quite old and predates organizations such as it. Almanac offices got it starting. And these are astronomical almanacs. And the reason they got it started is that they were a regular product. They were ephemerides that were used for surveying and navigation in the 18th and 19th century. They had to be done, particularly for the navigation part, 3 to 5 years in advance so that when you left Europe on a long voyage, you would have a star chart that was still accurate. And they first experimented with how do you take a large single computational problem and divide it. The picture is of the British Nautical Almanac Office, which was the first, 1768. Babbage was involved in it. He served on a board of overseers for it during the 1830s. And there's an example of its early product. They used the tools of factory management of their time. In fact, it's no coincidence that the start of the British group coincides with the start of factories in the Midlands. They read the same books. They used the same ideas. And the fundamental thing was you had common methods, common tools for computing, common input, common product, and a common location to work together, particularly the location so that the computers could train each other and get them up to speed. They also had a fixed management plan and methods for controlling information. And if you look, and I've been told I have a button. Yes. Okay, that red rectangle, that's the information control device. That was a set of racks, each with different projects on them, where partially completed calculations were put for others to pick them up and use them. And so all the additions would be done, as much as could be done. Let's give them to the subtractors. Let's give them to the multipliers. So that process was in there. And what's also interesting is that it relied heavily on the managerial theories of its time. The leaders followed the ideas of Frank and Lillian Gilbreth, who in management theory are very important. They also had a son who wrote a very funny book about them, which is useful. And their student, William Henry Leffingwell, who described information flow in offices. These were the places where those ideas were being discussed. Now, if we go back to that one group, the Math Tables Project, it is an offshoot of the Institute for Advanced Study. That's important because that's where von Neumann was. The institute's formed in 1931 by a group of academics funded by a large retailer in the United States. And it was primarily a school for Einstein, a place for him to come in the United States and get out of Germany. But it also had von Neumann, it also had the American Oswald Veblen and two other mathematicians. It was located at Princeton University, and it still remains an important institution in American intellectual life. Veblen became the leader of the American math community. He was trained at Chicago. He led a computing office in World War I that did ballistics calculations, very interested in computational physics. In founding it, they found a general director who had been an assistant at the Institute for Advanced Study, Arnold Lowen. He had a PhD from Columbia, very conservative PhD, I would say. It's probably 20 years. It would have been current 20 years before he got it. He served as an assistant for 1 year, as they all did. And he, too, had difficulty getting a job. He had trouble in that he was Jewish, and most universities were at least partially closed to Jewish faculty. But he was also a difficult person to get along with, and that didn't help his case in the least. There was no permanent employment he could find. He worked for a time as a manager of an incineration plant. And he took the work relief project, as did Gertrude Blanche, because it was one of the few jobs he could get that was involved in his field. None of the serious mathematicians of the time would initially touch it. He kept contacts at the Institute. He wrote regularly to Einstein. He wrote regularly to von Neumann. He asked for advice. He gave suggestions of things he could do for them. So it's clearly very much part of that world. However, von Neumann was polite in his replies, but it was kind of those replies of, thank you for telling me what you're doing. It's so good to hear from you. I will get in touch when I need you. And I'm sure that will be soon. And that's all he ever said for much of the time. And as I said, I think Lowen was pushy, and he was difficult to get along with for some people, and I suspect that was the problem as much as anything. However, von Neumann had a friend in England named John Todd, who was a mathematician, young mathematician employed by the Navy. Todd happened to be married to Olga Taussky. And I knew John during his last years, a lovely guy. And I think I am doing him no disservice to say that he was very aware that he was known as the mathematician married to Olga Taussky. She was the star in the marriage. He was a good guy. He was skilled. He was competent. She was Olga Taussky. And he went where she went. He supported her and was very loyal to her. That meant he did things that he might not have done otherwise. In particular, he stayed in England and he worked at an organization called the Admiralty Computing Bureau. He led it, which did ballistics, waves equations, the equations for degaussing ships, which was getting rid of magnetic fields so you didn't trip off mines. It was smaller than the Math Tables Project, but it had a longer heritage. It went back. It could trace its roots to the 1878 Greenwich Observatory Computing Organization. Von Neumann visits the group in April 1942. Todd invited him to come to see what was being done for mathematics in the Navy. When he was in London, von Neumann said, sure, something he never did, to the math tables project, an hour and a half away by train from the Institute. This group was then housed in Bath, so the two of them get on a train from London and go out to Bath. As they did it, von Neumann said, how do you divide problems up? How do you make it possible to take one calculation and give it to 12 people? And the two of them sit on train. Todd describes it in a method that would be familiar to all of us because it looks like a spreadsheet. And in that conversation, the two of them, step by step, abstracted the idea and got something very close to the modern program, with lists of instructions, jumps back and forth, and calculations to be done. They even worked out the basic ideas of flowcharts at the same time. Now that becomes important about a year and a half later, when von Neumann, who is then working at the US Army and doing ballistics work for them, meets Herman Goldstein at this railroad station in rural Maryland in the United States. Herman Goldstein recognizes von Neumann, comes up to him and says, hi, you don't know me. I'm a person who hopes to become famous by being your assistant. Can I tell you about the project I'm working on in computing machines and what we're doing? Von Neumann immediately takes interest and agrees to come visit. That project was, of course, the ENIAC. It was located at the University of Pennsylvania. It was doing ballistics calculations, primarily anti-aircraft fire. It was a very complex machine, 18,000 tubes, or valves, as they're often called over here. Had a very different structure, nothing like what would become the von Neumann design. It was not operational when von Neumann saw it. And also it looked a lot more like the math tables project than it did the modern computer. Von Neumann, in getting there, immediately does what Herman Goldstein said. He looked at it, they finished off the design and lost interest because von Neumann saw it a different way. He reworks the design in a paper called the Draft Report of the EDVAC. Goldstein was the person who actually did the draft. It's in his hand. But he and von Neumann were in constant communications, and this was the opportunity to get the idea caught up. And in the process of this, they put together the first description of the von Neumann architecture. It's vague, it lacks many of the details, but it's the first time we see the modern computer. Now, in the process, this becomes quite controversial because it shows how von Neumann works. He went to activities, he saw things, and he immediately elevated them, abstracted them, generalized them, and provided a foundation for more work. And that's exactly what he did here, except there were 4 people there who had been thinking about these problems, and they weren't mentioned, and they were quite angry at the process. So angry that when I would interview them later in the 90s and the end of their life, they would still be bitter about this, 50 years later. This starts von Neumann's computer research. He gets money from IBM, from a variety of sources, and builds a computing lab at the Institute for Advanced Study. This first of 3 papers is called the Preliminary Discussion on the Logical Design of Computing Instruments. It is the first discussion of what is now the von Neumann architecture, and it's much closer to the modern conception of what a computer is. One of the interesting things, though, is this paper, and the breadth of ideas in it is just quite stunning. Introduces the idea of flowcharts and says this is a great way to describe computing and computing programs. And of course, the idea of flowcharts at that point was 20 years old. It was in a paper by the Gilbraiths in 1921, used for factory management. Goldstein knew that, von Neumann knew that. They didn't feel the need of talking about it because they were moving forward. Now, I don't want to, out of the process, talk about the issue that von Neumann is taking others, but this is part of what he does. He sees things and moves forward. His computer was built here in what is now a child care center at the Institute for Advanced Study. 3 elements, 1,700 tubes, and it produced 21 derivative machines, the most important of the lot being the IBM 701, because that's the machine that gets copied again and again and again in the computer industry. During this same period, von Neumann is serving as chair of a committee on high-speed computing devices at the US Academy of Science, which operates a little bit differently than this academy does here. It views itself as an advice on science and industrial planning primarily. The debate they argued about in much of their thing is, what is computing? What is computer science? What are we starting here? And one of the conclusions that they came up with was that this was something they wanted to pursue, and there simply was not enough talent in the United States. And because of that, they needed to limit their vision. And von Neumann immediately rushes out and ignores that fact. The computing groups, however, were being disbanded at this point. The Math Tables Project was restructured, shrunk, moved to Washington, D.C., and was doing far less than it had done just a few years earlier. Von Neumann, however, at this point, did ask for one problem, and that was another problem he had been working on, linear programming. He took the problem, which was you have 88 food items, you're trying to satisfy some basic dietary requirements, and what's the minimal cost? Divided up amongst about 30 people. It took a month to do. Von Neumann had wanted to do it on the ENIAC, but he couldn't get access to it. So he did it on his own with this group, and the back of his notes show him translating the work that they were doing into what the ENIAC would do and how fast it would operate. World War II, however, had demonstrated the need for these groups, and yet they were being viewed as being in the way of electronic computers. There are a number of early papers in the late 40s and early 50s where people say we've got to get rid of them because we've got a better method and we want to support that. Von Neumann was dismissive of the groups at this point, saying, you know, they're doing very simple things. He really wasn't concerned about what the workers who had been trained might do. He didn't worry about the methods, in part because we ended up being able to use much more efficient methods for electronic computers because we found it easier to do long division. And so he was generally willing to let the groups go and die. And this picture, I think, somehow summarizes it. This is actually Gertrude Blanche from the Math Tables Project. And this is her view of the electronic computer installed in her office. Not something she was pleased to see. She never mastered programming. But by 52, she and others were beginning to be aware that ordinary scientists, ordinary engineers would not have access to computers. And they were talking that perhaps it would be 20 years. And at some level, they were right. Microcomputers, mini-computers in particular, are an early 70s thing, and largely were not unavailable to the ordinary professor, the ordinary engineer, the ordinary scientist until then. And there was a need to retain skills and codify the methodologies. That took place under the direction of John Todd. He got a group together, largely alumni from the Math Tables Project, and produced a book that is commonly called AMS 55. I refer to it as the Handbook of Math Functions. It's one of the largest selling books in the scientific literature, in part because they almost gave it away. But it's largely the work of Math Table Project veterans. This comes out, this work, this last resurgence of computing groups, comes just as von Neumann dies, and really his death ends the first stage of the computing era. We're now seeing companies involved, universities are starting to build programs in it. We are starting to see systems of how you approach the subject evolve. The industry was healthy. There were roughly 4,000 computers in 1964 in the world. And that meant there were enough people who had ideas, who could share them, who could talk about them. There were the ACM and the IEEE were starting to make preparations for a standard curriculum. And step by step, we were seeing the growth of the field. The field, and this is another measure of it, this is Gertrude Blanche again on the left, shaking the hands of US President Lyndon Johnson in '64. This is an evidence of sort of the shift, when the influence of this group started to wane, of the computing organizations. And it says, I think, some fairly fundamental things about von Neumann, about computers, and about the world in which we lived. About electronic computers, it points not to the influence of these hand workers so much as the influence of industry. It was the means of getting the ideas of factory management into computing. And if you think about it, computers were then, and still are now, a capital good. They replaced labor. They extend labor. And they, as a capital good, are more like a factory than an individual product, particularly when you start thinking them, as von Neumann did, as self-replicating automata. What does it say about computer science? Well, again, that's the point I made at the start. It has taken and absorbed ideas from virtually every part of human endeavor. And it really shows that one of the foundations we just don't acknowledge as much as we should, is really the idea of industrialization, industrialism. The basic steps of industrialism were taking manufacturing products, analyzing them, abstracting them, sequencing them, synthesizing the results, and putting them in one place as a factory. And that is actually what we do and is the foundation of what we now describe as computational thinking. It is something that is part of the Industrial Revolution, not something that's particularly new. So what does it say about von Neumann? Again, points to a credible range of intellectual skill. It also points to a certain egalitarian approach. He took all ideas. He took things that were of interest to him. And when he needed, he would take a look at them, abstract them, elevate them, look for ways to generalize them, and find, as I said before, putting them on foundations that led to more kinds of results and greater utility. He did have a little bit of a weakness. He didn't often regard who was working in the field already. As I said, I don't think he stole it and didn't intend to. It's just he got there, he saw it his way, and it became his way even when others were there ahead of him. Ultimately, I think the piece that it says about it is it resituates where von Neumann lives, going back to the idea that he was one of the aliens that came from Hungary to the United States and just was a born genius. It points to the fact that it's not so important that we live in his world, which we do. We live in the world of the computer, which he largely outlined and described. It's that he lived in ours, and he responded to the elements of ours. And he wasn't working in an abstraction that was disconnected from how we live, how we work, how we produce things, how we manage the information of our daily lives. He responded to common ideas, and he responded to the world around him. And that is the von Neumann that I would like to leave with you on this talk.
Thank you for this presentation. Beginning, I mentioned that the Neumann Society is focusing the history of the computing, but your presentation was very inspiring because it's not only equipment history, but is a, let's say, history of the institutes, history of the people, and history of the society. And I think it's very, very inspiring because Hungary is focusing mainly the equipment, and you help to make a wider view. And would like to thank you the presentation. This is the medal of this year, and I hope that you can. Thank you very much. Okay, the next is a video presentation because of the capacity and security reason. We are not able to connect online with the presenter, and therefore he sent his presentation on our video. The next presenter is Peter Denning, who is a professor at the Naval Postgraduate School, and he's best known for pioneering work in the virtual memory and working in this field of development, and his presentation on the topic is computational thinking. And please show the video.
Hello, this is Peter Denning, speaking today about computational thinking. Let me begin with introducing myself. Who am I? Well, I'm a computer scientist. I've been a computer scientist since 1964, and I've seen a lot of computer science come and go. I've done work in virtual memory, operating systems, performance evaluation, internet, computational science, and innovation leadership. I've taught computer science at MIT, Princeton, Purdue, George Mason, and Naval Postgraduate School. I founded a research institute called REACS at NASA Ames Research Center, specializing in computational science. I've published 13 books. The three most recent ones, images are shown here. The Innovator's Way is about leadership practices for producing adoption of innovations. The Great Principles of Computing is about just what it says. What are the fundamental, timeless principles of computing? And computational thinking is about a specific practice of computing called computational thinking, and that's the topic of the rest of this discussion today. Well, this is at a conference for John von Neumann. He's one of my heroes in history of computer science, foundations of computer science. He was a polymath. He was a virtuoso at calculation. He saw advanced calculating machines as essential for progress of science and technology. He is responsible for the von Neumann computing architecture, which is pervasive in all computers today. He saw many parallels between brains and computers. This topic fascinated him. Could computers be brains, was one of his questions. I don't know whether he ever got to an answer for that one, but I do know that he was an inveterate computational thinker. Well, what is computational thinking? Well, I use the abbreviation CT for computational thinking. One of the common meanings of it is a K-12 education movement started around 2006. The other meaning of computational thinking is just the disciplines of thinking to design computations well. Well, let's talk about the definition of computational thinking. This is something that's evolved over the years. In the 1960s, when the first computer science departments were being founded, computational thinking was called logical and procedural thinking for computer methods. In the 1980s, 20 years later, it was advanced quite a bit. It was seen as a third way of doing science. Up to that point, science was seen as advancing through theory and experiment. Beginning in the 1980s, science was also advancing through computation. In 2006, we'll come back to this in a moment, there was a milestone. Jeanette Wing published an editorial on computational thinking, and there she defined it as thinking like a computer scientist. A few years later, around 2010, there was a kind of consensus that said computational thinking was formulating problems so that their solutions can be expressed as computational steps and algorithms that can be performed by information agents. And then at the modern time now, computational thinking has two distinct meanings. One is designing methods that get computers to do jobs for us. And second is explaining and interpreting the world as a complex of information processes. We should note that computational thinking is not the same as computer science. Computer science, CS, is the field of study of information processes, both natural and artificial. Let's look at the history of computational thinking. It actually goes way back before the beginning of computer science. In the ancients, millennia ago, the ancients talked about math-based algorithms and methods. For example, Euclid's algorithm comes from that time. Much more recently, around 1820, Charles Babbage proposed a difference engine to compute tables like navigation tables for the Navy to avoid human errors. Human errors in the table were common, and the difference engine was going to be able to create those tables without any errors. Babbage was having trouble implementing it and conceived of a more efficient design, which he called the analytic engine, and it was actually designed for general computation. This was around 1840. He formed a partnership with Ada Lovelace, and they looked at all sorts of issues around the analytic engine, including how to program it. She came up with one of the first computer programs, and she also speculated that this machine was much more general than doing arithmetic computations, and she called it the science of operations, the ability to manipulate any kind of a symbol with this machine. Much more recently, the United States Air Force published a description of ways of thinking for information technology professionals. What would they need to be successful? Near the beginning of computer science itself, the pioneers Alan Perlis and Forsyth talked in terms like algorithmizing, meaning creating algorithms, and procedural methods as characterizing computer science. Papert was the first to actually use the term computational thinking in 1980 in one of his books. He kind of did it in passing and didn't actually propose it as a definition at that point. Then in the 1980s, computational science grew up in the other sciences outside of computer science, and computational thinking was seen there as a new way of doing science. Computational thinking in education has also evolved. This is within the computer age now. The first attempts at this were called computer literacy in the 1980s. There were a lot of courses proposed to teach young people how to be literate users of computers. They were not terribly popular. Then this turned into what was called computer fluency. It's like learning a language and becoming fluent in it, so you can not only do the exercise, but you can design in it and explain in it. That came in the 1990s. Then in 2006 came the Jeanette Wing editorial, which brought computational thinking to the foreground as a way of teaching computing to young people. And shortly after that, the National Science Foundation adopted this idea and was an advocate of it and put substantial resources to promote it in the following years. Well, let's talk first about when we talk about teaching computer science or computational thinking, CT, curriculum, what are we talking about? What are people teaching here? Well, generally speaking, we're talking about skillful practices of thought and design. We're not talking about concepts and methods, we're talking about practices. This means as you practice them more and more, you get more experience, you can get better and better at them. There's a spectrum of practices you can learn, which goes from computational thinking for beginners at the left end to computational thinking for professionals at the right end. Computational thinking for beginners has a whole list of things that people want to teach kids there. in various ways. There's a lot of discussion about in the education community about how to do that. But the topics they want to cover are abstraction, data collection, data analysis, data representation, algorithms and procedures, problem decomposition, automation, parallelization, and simulation. That's a pretty crowded curriculum, so the curriculum for the younger people kind of ends there with this list of topics. When you get into higher education, you start learning all sorts of additional topics which are much more advanced than what the beginners learn. I call these CT, computational thinking for professionals. As to be a practicing professional, you better be good at many of these things. So these include neural networks, artificial intelligence, computational complexity, software engineering, operating systems, networks, graphics and images, distributed computing, and performance modeling. I think you can see there's a pretty big difference between basic computational thinking and this advanced kind that professionals need. So the computational thinking for beginners is associated with the K-12 education system, and computational thinking for professionals is associated with universities, graduate school, and also with professional experience. Well, computational thinking also comes with various misconceptions about it. For many people, it's a new idea. They hadn't thought about this before 2006. They're relative newcomers to computing. They didn't know there was a long history behind it before it came out and started an educational movement. And so the people who've been describing computational thinking and proposing what we need to study have included various misconceptions about computing in their curricula. And I put these in two categories: annoyances and big deals. Annoyances are misconceptions that are, minor annoyances. They don't cause serious trouble, and they're probably pretty easily cleared up by talking to people about them. The big deals are more serious misconceptions that actually mislead people. If they're trying to design software or design new hardware, they can get things wrong. And the programs they create have errors in them, don't perform as expected, and can create harm. So let me go into some of the examples of this. Among the annoyances is a belief that computational thinking is a new approach to problem solving. Well, I hope you can see from the very brief summary at the beginning that there's a long history going back 1,000 years of people using computation as an approach to problem solving. So this is not a new approach, it's an old approach to problem solving. We've obviously enhanced it in the modern age because we have the new tool, the computer. But it's the idea of thinking computationally is not a new idea. The second annoyance is a belief that everything you need to know about computational thinking is in that basic computational thinking foundation, which I was calling CT for beginners: abstraction, recursion, etc. Those basic things, which are actually basics of programming. So it's not true that to be a computational thinker, that's all you need to know, especially if you wind up growing up and going into a profession. You're going to need to go way beyond that and learn what I was calling computational thinking for professionals. Another annoying misconception is the claim that computational thinking is for everybody. Well, I can think of many, I'm sure you can too, think of many people who don't particularly want to use computers or computation in their work, so they don't think about it. So they don't need to know this. They would, if you tried to teach it to them, they'd probably say they're not interested. So this is not necessarily for everybody. A fourth misconception is a claim that it's nothing more than logical thinking. Logical thinking simply means the ability to decompose a problem solution into steps and then specify the problem solution as a series of steps that follow logically from one to the next. And so being able to do that is called logical thinking. However, computational thinking also includes much more important, larger tasks than simply putting together instructions in a sequence. It has to do with design. How do you design a software system that has requirements and you can demonstrate to the users that it meets the requirements? How do you organize a software development project with hundreds or thousands of programmers so that it successfully deals a very large application that works? So there's more to computational thinking than logical thinking. Another annoying claim is this one: computational thinking means to think like a computer scientist. Well, you can certainly say a computer scientist is a specialist at computational thinking, but it's also, if I were a physicist or a chemist or an economist or somebody in another field, I might say I don't particularly want to learn how to think like a computer scientist. I have enough trouble learning how to be a good thinker in my field. So not everybody wants to think like a computer scientist, yet computational thinking is valuable to them in some forms of their problem solving. So those are the annoying claims. Let me now take a look at the bigger ones that can actually cause harm if people actually act on them. One of them is an ancient problem with computer science, is the perception that computer science equals programming. So in other words, if you can learn how to program well in a programming language, you have learned computer science. Well, programming is one of many areas of computer science. There's many other areas like algorithms, data structures, and getting even farther from programming is graphics and operating systems and databases and networks, software engineering. There's many things that go way beyond programming, and into design of computers, into design of computations. So this is a dangerous perception, and unfortunately has plagued the field of computer science for many years. And we thought we had defeated it some years ago, but this misperception is coming back with computational thinking advocates unwittingly promoting this idea. Another big deal thing is that computational thinking is about algorithms, and machines play a minor role. So in other words, the idea is that an algorithm can run on any machine, so machines don't matter anywhere near as much as algorithms. However, when you think about it, this claim doesn't make any sense, because you can't run an algorithm without a machine. The way we have been taught to think about algorithms, at least since I went through a programming curriculum, was an algorithm is a step-by-step procedure. Well, that idea of step-by-step procedure has been around for a long time and is built into the so-called von Neumann architecture, the big contribution of John von Neumann. The idea that there's a program counter in the machine and it clicks off one instruction after the next is part of the machine. And this has colored the way we think about algorithms. We have new kinds of machines arriving today, neural networks. Among them, biggies, big type of machine, which doesn't, a different type of machine requires a different kind of thinking altogether. It doesn't involve step-by-step thinking anymore. So CT is not about algorithms. Machines has to be part of it. The architecture of machines has to be part of it. As I just mentioned, the definitions about algorithms and programs we have in our programming books implicitly assume a von Neumann architecture. It implicitly assumes there's some computational agent going through it one step at a time, following the logical sequence given in the program. Well, this has been a very powerful notion, has survived for many, many years, since the middle 1940s. And now, today, we have new kinds of architectures appearing on the scene, which are not von Neumann architectures, but which are very important, and we can't think about them in this step-by-step manner any further. We need to think bigger. Another misleading claim is that human and machine information agents are equivalent. And this is based on the idea that once we have an algorithm written down, a machine can follow the steps, but so also can a human. And what's the difference? Is, well, the machine's going to be faster and the human's going to be slower, but in the end, they both carry out the computation. Well, this is also a very misleading conception because it's just not true. They are not equivalent. Humans can do small algorithms and small programs. Machines can do fast algorithms that are very fast and very large compared to anything that a human can do. I like to think that a fast-thinking human can do about 1 calculation per second, and a fast machine can do 1 trillion calculations per second. This means machines can do things that are impossible for humans to do. And in fact, that's one of the reasons we have machines, is to do tasks for us that we can't do ourselves simply because we don't have the capability or the time or the resource. So the machines are useful because they are different from us, not because they are equivalent. Sometimes I've heard this claim here: computational thinking is a replacement for computer science. Well, again, this is a misconception about computer science. Computer science is so much bigger and so much broader than programming and algorithms, which is the basic idea of computational thinking for beginners. So computational thinking is not a replacement for computer science. At best, you could say it's a component of computer science. Another misconception is computational thinking transfers to all domains. So what this means is that if you learn how to program, say, or learn how to solve problems computationally in computer science, in a computer science course, you'll be able to take that skill to any other domain. So you could take it to physics or chemistry or aerodynamics, mechanical engineering, economists, whatever. Well, this turns out not to be true. There's researchers actually studied that, and they've disproved this. It does not transfer. You need to have domain knowledge. So a computer scientist who wants to collaborate, say, with a aeronautics engineer needs to know some aeronautic engineering and some aeronautic science in order to be an effective collaborator. So just simply having the programming knowledge is not good enough to be able to go work with people in other domains. You have to learn something about their domain in order to be able to collaborate successfully with them. So computational thinking can assist in other domains, but it doesn't just transfer over. Another claim is computational thinking applies to all problem solving. So give me any problem and I can find a way to deal with that problem computationally. Well, that's not really true. That's an overclaim. there's lots of things around that we call problems that have nothing to do with machines and computation, like social problems, for example. And so computational thinking does not help us with that type of problem. Another claim is computational thinking is timeless. It's bringing out timeless basic principles and is not affected by emerging technologies. Well, that is also nonsense, because we have several new emerging technologies today, such as artificial intelligence technologies, the machine learning, the neural network, and we also have the emerging quantum computing. These are new kinds of technologies. They're programmed in a different way from von Neumann architectures, and we need to think differently about how to program them and design them. So we are affected by emerging technologies, and in order to carry forward, we need to constantly adapt computational thinking to the design problems and the technologies that are presented to us. Well, those are the main misconceptions. So for the future, I'm looking forward to, as we gain more understanding and more consensus on computational thinking, we are going to see that we will recognize that computation thinking is domain dependent, that it is different for beginners than for professionals, that it is a mental design practice rather than simply a set of concepts, and finally, it's different for different kinds of computers. You already mentioned neural networks, generative AI models, and quantum computers. Each of those is a different way of thinking about computation, and if we're going to use computational thinking with them, we have to train our minds in a different way. So, anyway, that brings me to the end of this discussion about computational thinking. If you are interested in this, you saw the book that I wrote with a colleague, Mehdi Tidra, on the second slide, and you can go get that book and read more about it there. But this is, in many ways, a continuation of the way John von Neumann wanted to think about things and use this kind of thinking for problem solving and design. And of course, in the book that he put together on computers in the brain, he was particularly interested in the questions of whether the brain could be a computer or a computer could be a brain, either way. And I don't know whether he's answered that to his satisfaction, but those questions are still with us today. And they still drive a lot of science and technology. Anyway, so I'm very pleased to have been able to talk to you for a few minutes on this topic, and I thank you for listening.
Okay, thank you. It's interesting that we heard that 80 years ago that the Neumann and similar started a new method, algorithm programming and that type of things. That today this is a teachable thing for everyone to know to survive in the future. It's interesting that from 80 years ago it was a scientist knowledge, and today it is every life need to every life. It is interesting approach, and after this video presentation, we have a next presenter is James Keller here, and he's a distinguished professor at the University of Missouri Columbia, honorary professor at the University of Nottingham, United Kingdom, and he is president of IEEE, Computational Intelligence Society. I hope it's a good summary. And His topic is that you can see we arrived at the artificial intelligence after the computer thinking.
Right, so
Please.
this is kind of, you always put sort of the light talk at the end, maybe, to get everybody sort of ready to go home. Right, so I was happy to come to this meeting and have something to say, but I thought, what could I add to the discussion? Because I don't work in an area that's directly founded by John von Neumann. So, you know, I'm sort of thinking, well, how am I going to make the connection, you know, to him? And I found out this morning that I'm one of those Americans who really didn't appreciate John von Neumann as the scientific genius that he was. And, you know, because I didn't hear about him much. I mean, I knew about the von Neumann architecture sort of as I was going through school, just more, but I didn't appreciate it well enough. And my story, though, is when I was studying for my PhD in math, I had to demonstrate that I could read mathematics in German. And so as part of the language requirements. And so I found a von Neumann book that had both a German and an English edition, and I used it to you know, check my translations, you know, and see if I could translate properly. And you know, and then another thing I learned this morning is that I was on one of those little tributaries that was far from the source. And so, you know, I probably should have paid more attention to the content of the book than just whether or not I could go back and forth. Anyway, so what am I going to do? I am the president of the IEEE Computational Intelligence Society, and but the buzzword today is AI. Right? Everybody's talking about AI. AI this, AI that. Is AI are we going to have an AI Armageddon? You know, is there going to be Skynet all of a sudden, and you know, and humans are going to be destroyed? And there's an interesting, by the way, if you get IEEE Spectrum or you have access to IEEE Explorer, I don't know if it was just the most recent one, they had a nice 2-page article about many famous AI scientists today and where they sit on the AI Armageddon. You know, whether or not they think, first of all, AI is going to become a generally intelligent agent or not, and then whether it's going to cause destruction of the human race or not. You know, and it's interesting to see who fits where in there. You know, anyway, so that's in there. So my intention today is dissect is too big of a word. You know, I'm going to look at both artificial intelligence and what we say computational intelligence is, and hopefully like look at some of the thoughts and accomplishments of Drs. von Neumann and Turing in this AI timeline, sort of how they interacted, what their, you know, from what I could gather, what their thought processes were, where they fit on the AI spectrum, and then of course, how do these large media models like ChatGPT or DALL-E, you know, or many others now that are out there. I mean, I found out now Photoshop has one. Word is going to have one soon. I mean, it already does projections of what you think you're going to type. Where do they fit into this picture? And in particular, I'm going to tell you what I believe would be the reaction of these two guys to ChatGPT, you know, in there. And it's just all pure speculation. So, you know, I mean, you can disagree completely, and that's okay with me. You know, just don't throw anything. And this is more, you know, I put this last bullet in there because it's really about me getting ready for this trip. You know, it's my meandering, you know, thought processes. And so I realized after I submitted the final version of this, I realized that I've repeated myself in here a few times because of different quotes I found in different places. And so just have to bear with me. So first thing I want to talk about is artificial versus computational intelligence. And so, you know, I mean, is it really a big deal? Because you've got AI, and then we of course, are the CI, you know. And so the guy in the back there points out that it depends on whom you ask this question to, whether there's a difference, and when you ask it. You know, so I wrote an editorial in our magazine about what's in a name, you know, whether AI and CI are really different. And so, of course, everybody's talking about AI now. You know, it's AI this and that. Everything we do now, if you can say, well, this is really AI, you know, you get, you know, it's good for funding. But of course, what is it? And so when I was a kid, academically speaking, you know, and I got into the electrical engineering department, and I was told, you need to teach a course on AI, you know, inside EE. And so I knew what it was at that time, and it was formal logic, basically. It was systems with propositions of discrete symbols manipulated through first-order predicate calculus, and maybe sometimes you had some probability, but it was always on the side. You know, you would do some probability calculations of the rules, and then you would report that separately. But the rules were all crisp. It was formal logic, and so that's what I taught, you know, till I found a book that also had the word AI, but it was really pattern recognition. And I thought, oh, I like that better. And there were languages that were built and machines that were built specifically to manipulate propositions of symbols. So you know, we had some symbolics machines, you know, very expensive for what they could do. I mean, but they ran Lisp in hardware, you know, and so it was that kind of environment that I thought, right? But when the IEEE, we started out as something called the Neural Nets Council in my gang, and then we became the Neural Nets Society, but they decided to change the name to the Computational Intelligence Society, and it made perfect sense to me that there was the difference between AI and CI, because CI, all of the underlying models for computational intelligence are based on numeric representation, non-symbolic representations, functional representation sometimes. So it was a nice crisp partition. Had AI over here, you had CI over here, and they won't meet, you know, in there, I thought. All right? And so the three pillars of our society as it's grown up are neural networks, fuzzy systems, and evolutionary computation, all of which are embedded with numeric representation. And we have a bunch of other related topics that come in here, including, for example, artificial life as part of, sort of spun off of evolutionary computation as a topic area within the IEEE. Right? That was supposed to be my symbol for that. I found those little digital bugs on the net. But was that ever the case, that they were really separate, that there was a dichotomy between these? And so then I thought, well, how far back should I go? So I went back to the place where AI got its name, right? And that was the 1955 proposal by John McCarthy and colleagues for the Dartmouth Conference, where they coined the term artificial intelligence as the science and engineering of making intelligent machines. Of course, none of that, I mean, it's a very circular kind of a definition. But in that proposal, the fledgling area of neuron networks were brought up. I mean, it wasn't the main result of the conference, as it turns out, because they focused mainly on symbolic logic, right? So that's one of the pillars of computational intelligence. So even back at McCarthy's time, the partition was never crisp, right? And in fact, it's not even a fuzzy partition. I'm you know, sort of my sub area within computational intelligence is fuzzy systems. It's not even fuzzy where you share belonging to either AI or CI, but they, you know, you can't, you still have a partition. You really have topics that have high typicality in both of them. For example, fuzzy systems, which came up in computational intelligence, really is one of the tools that people use in explainable AI now. I mean, you know, one of the big areas in AI is this idea of producing explanations, or being able to interpret what's going on, and fuzzy rules and fuzzy systems are one way to do that. So a former president of CIS, Pablo Estevez, said, hey, let's go survey people and see what they think is the difference, because we couldn't get a good definition. We were trying to, back in his presidency, he was trying to write a statement, definition. This is what CI is, right? And this is what AI is, and they shall never meet. So he did, and what happened is, you could imagine every possible configuration of a Venn diagram where you got one bubble is AI and one bubble is CI, and one's inside the other, one's, they overlap. Some people said they don't overlap, so it's every possible configuration. There was no consensus. So my position in that editorial was, don't worry about it. Who cares what you call it? Do good work, have fun. And if it helps to call something AI, fuzzy systems AI or evolutionary computation AI, go ahead and do it. I mean, we are the Computational Intelligence Society, but we are also the Society of AI. And I put these last three little bullets in there because even though David has absconded, since he was a past president of the Computer Society, is that there were 4 societies that got together to create the IEEE transactions on AI. Computer Society, us, System Man and Cybernetics, the Signal Processing Society, and then the Robotics and Automation Society also kicked in. And we also, the first 4 of those also have created now the IEEE Conference on AI, just had the first version in this year, in 23, and the second one will be next time, this coming year. And so I felt pretty smug, as you can see in the picture, that I kind of had this all figured out. By the way, that kind of shirt is what I'd rather be wearing right now, but I just somehow felt like I couldn't, but I guess I should have anyway. But wait a minute, that I'm being told, only back to 1956? What's the deal, by these 2 guys? So, I went back, I started doing a lot more reading. I've been reading and reading and reading and reading. And so, obviously, Alan Turing thought it would happen, right? That this would happen. And he, had the design of the universal computing machine. David, I just put a word in for you, but I mentioned everybody that you had left. That could compute any computable sequence, right? The universal computer, and his basic principle, his basic thought on this was that it was only a matter of time and a matter of programming, right? That in fact he proposed constructing. He said, well, it's hard to imagine programming a human mind, an adult human mind. So why not just construct a child's brain mind computer with lots of blank pages and then come up with some learning methods? Right? And he said, of course, obviously the reward punishment scheme is the obvious way to, that you might teach, but it's just too inefficient. So you needed some kind of intuition. You needed to have some learning methods that had intuition, which of course is nowadays, we're all talking about transfer learning, right? You learn a problem on a big data set, right, that's more or less similar to what you're doing, and then you transfer, right, into this. Now, I used to think that was all just baloney until I saw it works. At least for deep nets seems to work. But he never really worked that out. Right? I mean, these were more thought experiments at that time, from what I've seen. So he came up then, in that 1950s paper, he posed this question: can machines think? Right? And he said, well, both machine and think defy real definitions. So I need to find a surrogate problem to do this. And so he proposed the imitation game, right, that we've all heard of, even me, back even though I didn't know sort of what it all entailed, but we've all heard of the Turing test, right, where you ask whether or not a machine, well, first of all, it was whether a woman could imitate a man was the original thing he proposed. And then he said, well, replace the woman by a machine, right in there. And well enough to fool an investigator where the investigator would have at most a 70% chance of doing a proper ID in 5 minutes of conversation, okay? And his conjecture was that within 50 years, and with a storage capacity of 10 to the 9th, and that was, the idea of storage capacity back then was a little different than we think about it now. I wasn't thinking of bytes necessarily, but units, right? Of 10 to the 9th, it was possible. This was his conjecture in that paper, right? But it was mostly a thought experiment at that time. All right, so this is the standard thing, where you have the human and the machine and then the interrogator, right, being separated from them. But I like this version better, where you're introducing your boyfriend to the parents, and they just want to know, going to ask a few questions to make sure you're a decent human being, But how do you tell if the machine is really intelligent? So I started reading some bunch of other papers, right? And there's a lot of interesting work going on among the people who are thinking about AI, as well as doing AI. I mean, as engineers, we like to do stuff. We heard that early this afternoon, right? We're more vigorous than rigorous at times. And but the people who are thinking about it are struggling with ways to assess it. And I could not find, and maybe someone more knowledgeable than me knows this, but I don't think Dr. von Neumann had a recipe for detecting that. I couldn't find anything about the imitation game in any of his writings, even though he and Turing worked together for a while at the IAS, and he lobbied to get Turing a assistantship, I guess is what it was. But he didn't address the imitation game. And so the current researchers are split. This is interesting reading, that many on the pro side of these things being really intelligent, these new programs being really intelligent, say that these achievements give you at least a glimmer of reasoning, right? Because that's really what they were talking about. And on the con side, it's more cautious to, say that this is really intelligence that's going in there. I put the references that I've been reading down at the bottom. And so there was apparently, I didn't even know this, but apparently there has been a prize every year offered for an annual Turing test, and for the source said for decades, until the guy who sponsored the prize died and the money ran out. So this was right about the time these large language models came into being. The prize is done. Right? So there's no more doing that. And I guess the consensus is that the large language models like ChatGPT might win. I mean, because you don't have to fool every interrogator every time, right? You have to fool sort of the average interrogator with a probability of it, I guess, 30% of the time, right? So, and it's a short conversation. And so this group down here tested 1.5 million people. They played a version of the imitation game, but the large language models that they used, which I think was ChatGPT 4 in there, were sort of primed to act like a human. So they gave the ChatGPT a scenario. It says, your name is Mary, and you sometimes don't do calculations correctly, and you blah, 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 blah. And sometimes you're aggressive in your answers, and, they would prime this thing to act more like a person, and the players identified the AI program 60% of the time. So only 60%, right? Only? I thought that was actually pretty good. But, so they haven't quite done it, but you can increase the odds, they were saying, if you know something about the large language models, how they're trained. so you try to put it into a situation that's similar but not exactly the same as what they're trained on, and they'll just spit out what they're trained on. You know, and so that's really how someone who's knowledgeable can game that system, right? But that's really, I mean, what we're asking these language models to do is to use deceit in their training, you know. And so is that really a goal for whether these are intelligent or not? It's kind of like a parlor trick. And so I thought I would ask ChatGPT what it thought, right? So, I mean, right, about its ability. So this was my question to ChatGPT. Could you pass Turing's imitation game? And so what it did is first it gave me a paragraph defining what the Turing test is, which of course is the first thing it spits out, you know, is you know, because it's just giving you words one after another based on probabilities. Then in the second one it says, whoa, this is a tough test, right? And even though I'm an advanced AI model, you know, it depends on lots of different things, right? It depends on the complexity of the conversation, who the judge is, blah, 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 right? And then it says also, I can't do this real time, even though, I mean, that's a hedge, right? The third paragraph's a hedge, right? Because it's saying, well, I can't do it real time, so I can't definitely claim I can do it. But look at the last sentence. But if you have any questions, hey, you know, I'm happy to carry on a conversation with you, you know. So, I mean, this is what ChatGPT told me. So I'm trying to figure out what does this artificially intelligent robot see when it looks in the mirror, right? And so what it's really seeing, these things are trained on who? On us, right? It's trained on everything that they can scrape off the web and everywhere else, and it's trained on. So they're just a reflection of what we've already said. Right? And this is a pretty cool picture, I thought. You know, I created, but I got it out. I thought I could just go out to DALL-E and just give it a nice prompt. I wanted a DALL-E style painting, right? You know, I thought that was kind of cute, you know, to go out to DALL-E and do that, of an AI robot looking in a mirror, seeing a reflection of people, because that's the message I wanted to give. But I had to build this image out of several attempts at both people in a mirror, robots looking in a mirror, and then I had to use Photoshop and PowerPoint to actually get this to work. You know, so DALL-E would not have passed my visual Turing test in this particular case. Not that anybody else might either. Okay, and then I just as kind of wrap this part up is that these large language models, you know, have been shown to do really well on benchmark tests. I mean, they can take the LSAT, and you know, they can take the board exams for doctors, you know, things like that. And they can do really well on those things. And so now people are starting to look at these ways to try to measure a little bit more of reasoning, being able to get from one step to another. And this is a visual one where they show a bunch of demonstration pictures where they say, oh, take that first image, you get the second one. Then in the second column, same thing, and then show 3 more at the bottom and say, what would the output image be in each case? Most of us can figure it out pretty quickly. I don't want to put anybody on the spot, David, but anyway, it would be, you know, it's the kind of thing. And the tests that were run by this group, you know, of course, all these things are published on Archive. You know, it's like, oh, put it on Archive and then run on to the next topic, you know. So they're not, none of these are refereed. But the large language models did poorly compared to the human subjects that they tested with this. So how would Dr. von Neumann approach this topic, right? So I read carefully, you know, his book that was published posthumously, and a bunch of other articles about him. A lot of people have opined on this subject of his connection of, and we just heard it last talk, is, you know, the connection between the brain and the computer, right? And so, you know, a lot of this is going to be quotes that I lifted from the paper, you know, that I sort of thought about this. He says he was looking for a way to understand the nervous system from the standpoint of a mathematician, and he admits that it's just systematic speculation, right? Just his thought process and going. We heard about his thought processes earlier. It was much more cautious than Turing. I mean, Turing was sort of out there saying, yeah, it's going to happen. It's just a matter of having enough people to program a big enough memory, right? And we'll get it all. And so, you know, it was clear that he investigated these problems one by one, looking from the bottom up in there. And he said that the most immediate observation regarding the human nervous system, when he's talking about comparing the brain to a computer, is that its functioning is prima facie digital. So he says, oh yeah, the brain is a digital organ, but even though it's organized digitally, all of the complexities that we can handle as humans, you need at least there's an analog role or some kind of mixed role of analog and digital in this process, you know. And so, yeah, he made a remark. He said, oh, you know, because look, the artificial automata need very high precision because of the air propagation, right? And, you know, significant digits start getting lost if you don't have a big enough representation, whereas the nervous system has low precision, and yet we still do better at reasoning. It has much higher stability, the human nervous system. And so, you know, he concludes that there's some radically different system of notation than the ones that we use in mathematics, you know. And so he says you can't replicate human intelligence in a computer because evolution was needed to handle loads of uncertain and ambiguous information that we all deal with well. Oh, well, some of us better than others. And of course, McCulloch and Pitt's neurons had been defined and studied by the time he's writing this thing. So he understands these some models, possible models, digital models for the neurons inside of, you know, inside a machine. So he could dig down deep into the components. Right? He was also worried about the fact that you might not be able to use formal logic in there because to represent human knowledge, because this would lead to the curse of infinite enumeration. You know, and of course, as was pointed out earlier this morning, he was well aware of, and I realize now he proved the second theorem on the incompleteness theorem. And so, you know, realizing this bothered him, saying, you know, I think my impression is that he moved away from a purely logical approach to artificial intelligence in that case. And one of the examples he gave was an example on visual analogy. The fact, if you're trying to describe triangles, two rectilinear triangles, he said, man, there's just an infinite number of ways that you could vary them. You know, they might not actually have all complete straight lines. You know, they might, as you drew them, for example. But people would understand that they're triangles. You know, the angles might not actually be, you know, if you were drawing an isosceles triangle, for example, or a right triangle, the angles might not satisfy the right constraints perfectly, but people would get it. So if you were going to model all that, you know, you need something more than just formal systems of rules, right? And so what I took from what he wrote is that he thought that you could use thermodynamics, the air probabilities and thermodynamics, to sort of model a lot of this uncertainty in there. I'm going to come back to that in a minute. Yeah, so he says the operation of logic have to be treated that allow things that have very low probability to still be true. You know, and that was where he saw this inconsistency with formal logic systems, right, in there. And this author down here said, oh, well, I work in Bayesian networks, and so that's the answer, you know. But I got a question mark there for myself. And of course, we've heard again, and I've read that you know, he has defined this artificial self-replicating automata with mutation in there. So he's built the mathematical foundations for artificial life, right, in this idea. And, you know, and he didn't get to the next step, which was to breed the automata which had more complexity than the one that it came from. He's able to do the mathematics to understand the sort of how the genome works, actually, right, the human genome, but not how you end up with more complexity than you started with. And so, blah, 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 blah. Yeah, this is one of those places where I just said the same thing over again. But this was 5 years before Watson and Crick that he did it. As a matter of fact, one of those two guys, I want to say it's Watson, you know, said without John von Neumann, there would be no Watson and Crick. Because, you know, he built his automaton, the self-replicating automaton, had three parts. You have the functional part, the thing that actually does the work. You have a decoding section that takes a tape. This is kind of the reference to Turing thing. That takes a tape, reads the instructions, and builds the automaton. And then you have a device that takes the copy of the tape and inserts it somewhere else, right? And that's you know, essentially how the DNA works, right? So my take on this is that, you know, I was going to say the fathers of AI, but I read that you might call Turing the grandfather and von Neumann the father. I don't know, it just seems wrong. But somebody else thinks it's wrong too. Or else somebody else thinks it's right, and you know, I'm in trouble. But I see this. I see these as kind of two different ways to attack the problem. You know, Turing was the optimist of symbolic logic, formal systems. You know, and he was using a top-down approach, where von Neumann was looking at the mechanisms, you know, the underlying mechanisms, and seeing if you could put it all together and get to that. Actually, I would rather say is that Professor von Neumann was the father of computational intelligence than artificial intelligence, and that way you don't have to argue about father and grandfather, you know, which one's which. Because he pioneered the analysis of biological and artificial neural networks, part of CIS. His work on cellular automata founded the area of artificial life, which is part of evolutionary computation in our definition. Again, you know, you can argue with me about that, but that's, you know, this idea of mutation, you know, in there. And he understood and proposed models for dealing with uncertainty in natural languages. Now, he was looking at using the probabilities in thermodynamic systems, but that was all before fuzzy sets became available. I'm going to believe, whether it's true or not, I'm going to believe that he would have thought kindly of fuzzy sets as looking at a different kind of uncertainty that's more related to the vagueness of natural language, as opposed to the probability that such and such was true. You know, and anyway, that's I'm going to say it. And this idea that the nervous system has to have both digital and analog parts, it fits nicely with fuzzy systems because you have analog-like confidence values that you get from stimuli. You manipulate them via more or less analog operations, and then depending on the application, you harden it to a digital answer. Right? So what do I think these two guys would think of ChatGPT, you know, as an agent of artificial intelligence? Well, this is what I think. I mean, I think Dr. Turing would say, absolutely, it passed my test, right? Whereas I tried to make it not a complete thumbs down, you know, but my thought was always he's much more cautious about attributing these things to intelligence, and I think he would have seen it. And again, I'm projecting ChatGPT back, back into the early 1950s. Right? And of course, what do you think? So finally, I'm done. I really want to thank Emery and everybody for inviting me and letting me ramble on for a while. And of course, this is as good as Google can help me say, and thank all of you for listening. And I was going to say, is there any questions or comments, but nobody's getting them. So that's good for me. All right. But this was created by Adobe's Firefly insert, which is also a large language media, a large media program that's inside Photoshop now. But it was the same prompt. There's no mirror, nothing. I just couldn't. I just could not get those programs to understand the idea of looking in a mirror, and seeing something other than themselves. I mean, if they did look in a mirror, it was a mirror like I had in that picture that I showed earlier. But anyway, I'm done. Thank you.
Well, thank you, Jim. It was a really summary and final presentation. And thank you for coming and your presentation.
Thank you. And thank you for this.
Okay. This is a medal. I mentioned it. Yes, as it is the end of the conference. This is the long 1 year long journey, because I mentioned that 1 year ago we met the president of the academy, and it was the starting point of this conference. It was 1 year long preparation and discussion, and I would like to thank you for all the presenter or speaker for this conference, because I think it is a really contentful and really, let's say, good for memory for Neumann. And I would like to say thank you to leader of the academy and the staff of the academy helps to make this conference. I really thank you for the Neumann Associated team as well, who is working to make this conference that type of level. And I think that I mentioned this is part of the list of the event of this year. In this year, we'll be in November an IEEE conference with the Neumann section, again a scientific conference. The next event will be in Hungary. Every end of the September there is a so-called Night of the Researcher, and we are organizing a program for this one in the University of Óbuda, and many Neumann presentation as well. And if I mentioned your webpage, the neumann120.hu, there are many other program, graphics, reports, books, and others. And I mentioned artworks as well. You can see the artworks that the Hungarian artists make for this year. Remember, for this year, and this conference was in the morning was mathematics heavy, and the afternoon was the informatic easy. But I hope that it was the useful, because it's both sides of Neumann, the abstract mathematician side and the engineer side we can show. I hope that you enjoy this conference, and I hope that you can follow not only the Neumann Society, but other university and other IEEE and other institution events and works for remembering von Neumann. Thank you very much.